those models. But importantly, we should remember that when we compare these two observations, it's actually not a like-for-like comparison in terms of their spread. Anyways, you can compare them. We talked about different scores you can use, but I think we kind of like the continuous rank probability score, CRPS, or kind of an average rank of the data within the model simulations, like we saw in one of the presentations. So then your final product would basically be, first of all, a rank of where your observational trends are within the model simulations. And then we also discussed, Flavio's talk was a good example of this, where some of the observations, they fit within the model spread if you look across all the models, but if you condition on specific models, you might see that only half of the models actually contain the observations in their spread. So we also talked about, should we provide a metric of the fraction of the models that contain the observations to try to separate out that internal variability versus structural uncertainty in these metrics. And then we were kind of debating, and I think we didn't necessarily converge on how we feel about translating these numbers to there's likely a disagreement, there's unlikely a disagreement. So we left that as unsure. That's all we have.
Hi, so our group reduced the problem to kind of two steps. One is there a discrepancy, yes or no? And then one is figuring out some of the answers about why. So is that forced or internal, or is there a forcing problem? Is there an observations problem? And we kind of based our discussion around something like this comparison of observations with some different histograms of different large ensembles. As you can see here from this figure that Li-Wei Dong made. I feel like I've been getting the credit for this figure, but it's actually from Li-Wei Dong in my paper. So this isn't exactly done everything we were saying to do here, so we considered also some other things that you should be doing. In particular, thinking about the observations. So the index you're looking at should be measurable in observations. Maybe you need to do something, as we saw from Ray, about using some theory to find something that's measurable based on sea level pressure instead of some upper level circulation. You need to make sure you can aggregate the observations onto some common grid with the models, or, as Karen was just saying, sample the models like observations with some kind of observational emulator. Overall, we discussed a bit reanalysis and came overall to the understanding that it's useful but needs to be used with caution. You should use multiple reanalysis. You should know what's being simulated. You should use all ensemble members if they're available to quantify the uncertainty, and where possible, you should ground truth with actual observations. We also talked about the statistical testing, but overall, we thought probably the easiest thing to do is, as also Karen just said, to use some kind of just rank within the ensemble members, if you have a sufficient ensemble size for that. I think you don't necessarily need as large of an ensemble size for that as you would for isolating a forced response. This is just well sampling a Gaussian distribution. Maybe you need about 30 members for that. And it's important that you should be using a two-sided test because we don't know which direction the discrepancy should be going. Some general considerations. Our group actually thought that it would be a good idea to quantify the expected internal variability uncertainty based on the observations and the models in a common framework. So basically comparing something like the interannual variability or autocorrelation, maybe even the spectra. And then based on the work of Thompson et al. 2015, you can actually relate the interannual variance and autocorrelation to a trend uncertainty for future trends. And this could be a good way of seeing whether there's differences in the variability rather than just the forced response. I'll get back to that at the end. And that one other general consideration is you should be looking at the sensitivity of what you're looking at to the time period of the trend. This was all thinking about single indices that you could be comparing, but sometimes we also want to compare patterns. There you can take a couple different approaches. You can either do this grid point by grid point, but there it's really important that you understand the number of spatial degrees of freedom you're working with and adjust your statistical test appropriately. Or you can just take the approach of reducing your spatial pattern to some index, or such as by a pattern correlation with observations or some kind of spatial aggregation. Then finally on the why, the forced or internal is really a hard question. We thought this method of Thompson et al. To get the uncertainty in the trends from the interannual variance could be a good way of saying whether it's an internal variability problem. And I think this actually hasn't really been done So I think this is the low-hanging fruit for people to try this, even for some of the well-established discrepancies like the Pacific SST gradient and Walker circulation. And then otherwise, it's maybe a force response problem. There's maybe something like the force MIP type methods that could help, but I don't think they've been researched enough to really say everyone should go do this. I think it needs more work to understand whether they can be useful or not. And we tried to come up with what null hypothesis are you looking at when you're talking about force versus internal, and there isn't really a good null hypothesis. We basically expect it to be some combination of the two. And so happy if others have a better idea of what the null hypothesis should be there. Then for forcing problem, we thought basically test CMIP 5 versus 6, smooth biomass burning, emissions versus concentration-driven aerosols. Then finally, for is it an observations problem, we thought this is actually maybe something you should ask at the very beginning and look at the consistency between different products and say, is the trend you're even looking at larger than observational uncertainty? No, that's all. Thanks.
I don't know why this is always giving me so much trouble.
Yeah, hi there. So we tried to kind of lay out like a flow chart here. We essentially had kind of 4 steps in a sense in our process. So we had a bunch of things that we thought would apply kind of only really to the observations. So essentially in the kind of top left corner here, how to kind of prepare your PDF of the observations. Bottom left, things that really apply to preparing your PDF of the models. Bunch of things in the middle that we think apply probably to both of those, both observations and models. And then at the end, in the bottom right, kind of pulling it together to some kind of assessment. So we talked about lots of different factors. I'll maybe kind of go around and pick out some things we haven't talked about so much this morning. In terms of the observations, obviously a challenge is to kind of quantify the observational uncertainty, right, like the structural uncertainty. And we thought there was a lot of potential here for Bayesian frameworks, although it's something we need to think really quite hard about how we do that. Things can be really quite sensitive to the prior that you adopt, for example. Checking for kind of non-stationarity in the observations, I guess like the example Russell showed with the kind of changing coverage, things like that. In terms of preparing the kind of model PDF, we thought ideally we should do some kind of model validation, right? How well do the models behave in simulating the kind of things you're going to rely on. We talked about model independence, I guess. We know there's kind of a family tree of models, right? And so if we make a PDF of models, then, if we have 30 different models, we don't necessarily have 30 independent samples there. And so how much we should really kind of think about that. We thought the kind of pre-industrial controls are really useful for understanding the variability in the model, how many ensemble members you need. And then things in the middle that we apply to both things. I guess we want to think about kind of what's the resolution of the different kind of data types. Thinking about things like dynamical adjustment if you want to remove things that you don't care about and get a cleaner comparison of the things that you do care about. We talked in terms of kind of protocols, we kind of had a statistical protocol and a physical protocol, so are we getting the right kind of thing for the right reasons? That was something that kind of needed both coming together. We also talked about simulators like the others. Maybe one last thing to highlight kind of at the end when you're assessing things is kind of what we called multivariate discrepancies. So, maybe we care about factor A, whatever that is, global mean temperature or something. And if we get some overlap in the PDFs, then we should maybe then go back and say, well, in that overlap, can we only get factor A right by getting something else wrong in the models? I don't know, like the Arctic or the tropics or something. So yeah, that's our plan. Thanks.
Okay, group 5.
Hello, for Group 5, our prescription for best practices in this problem comes separated into 4 aspects. First, what do we do about the observations? How do we think about them? How do we think about our models? What metrics do we come up with to compare both of them? And finally, how do we communicate those results? So first of all, for our observations, one important point that was raised is that we need to not only use as many observations as we can, but when possible, we need to validate these global observational products and compare them against the in situ station level data or whatever is available. The other thing that has been also mentioned by other groups is do model emulators to see if our model was measuring the same way that weather station does, what would it see, and really put value in that type of comparisons that can help us get to a deeper level in seeing what's wrong or what's right about the models and understanding the mechanisms. So then when working with the models, we came up with several important points. One is to use large ensembles wisely. Someone said yesterday, you don't want to run 500 members to get the right statistics of the wrong number. And I think that's something important to keep in mind. So assessing the variability, also being upfront about the mean biases of models and what that might mean for our mechanisms and statistics. Then compare apples to apples, sort of going back to the sort of ground truth level comparisons, and also I guess sort of going back to the observations a little bit. It's very important to know how the measurements actually made, and whether the variable in the model is the exact same thing as the observation is giving us. So yeah, apples to apples comparison. And also very important, as others have mentioned, considering sensitivity to everything that goes into a model, which might be a huge, terrible can of worms, but I mean, some of the important factors, the forcing and inputs for a model, but also model choice. So going through multiple versions of the intercomparison projects, etc. And yeah, that's important. Also doing out of sample testing to know when one model is really biasing our results in undesirable or unrealistic ways. And one last point, understanding mechanisms might be as important as quantifying trends. So the issue came up of if our model matches the observations well, but it does so for the wrong reasons, do we have a discrepancy, right? So that's the sort of reminding ourselves that we cannot reduce this whole problem only to statistics, because numbers can lie sometimes. So when we have our observations and models, then go on to the metrics. As some people mentioned, test the sensitivity for the duration over which you calculate your trends. You gotta be honest about that. Do good statistics. Be aware of your degrees of freedom, autocorrelation, cherry picking and multiple testing are important issues to be aware of. It gets complicated, but we gotta do it. And whenever we come up with a new metric, we gotta make the code available for other people to do so with, to calculate that metric with whatever observations or models they have. That's very important. And there are some packages already available for this, so whenever possible, got to use that to have some standardized form of looking at this problem. Then we liked some of the comments in the talks that we saw yesterday and the day before about ranks and probabilities. And yeah, reducing noise in any way we can. If it's justifiable, it's great. And lastly, when communicating our results, so ranks and probabilities are very useful for scientific inquiry and for doing science, but then coming up with works like likely, unlikely, that might be more relevant to application and communication to the general public, so know when we got to prioritize one or the other. Also the importance of publishing things models do right, not focusing only on the things that the models get wrong, and null results. And lastly, to also value publishing thorough data set descriptions that might not directly address the trends that we're interested in, but that might help other people understand where our data sets are, what our models show beyond what we want them to see about them. So all the boring figures that you have in your Google Slides, you know, make them available somewhere, because they are the foundation of the exciting results that end up in papers. So that's it. Thank you.
Okay. I think that's it. We do have for in-person, we do have a virtual room breakout summary. If there's someone online from that group that would like to present the slide, I would appreciate you unmuting yourself. I'm actually not sure who provided the slide.
Is Kevin is there?
Oh, great. Yeah.
Yeah, if Kevin is there, he can present.
Okay.
Otherwise, I will present. Okay, so we were the virtual room. We discussed the topic, among ourselves. Although we covered some of the same point as you have heard previously, there are few additional points that we also covered. I think one was use of the initialized run, including there were some discussion how the error that develops in a first kind of few weeks, how that might impact the trend. A important reference was cited by the Steve on Wu et al, where they saw like, yeah, if they remove the aerosol forcing, they found some improvement in that multi-year to decadal prediction scale. So that's kind of one way how to capture or identify what's kind of a level of uncertainty can be in the force response. We also a little bit delve into going into the higher resolution model that and how does it impact the trend or better capture the trend. There was quite a bit discussion on the forcing uncertainty. I think Gavin has a long list. I can talk about a little bit about the land use. Even for example, land use is the same data set provided to every CMAP model, and then when it gets specified into the respective model, they will give you kind of different graph cover, for example. So yeah, there are other forcing uncertainty that is listed here. With respect to the internal variability, we do agree with the previous discussion using the large ensemble. We also identify some of the talks Smith he gave about the signal to noise ratio paradox, or how it can be used to constrain the model projection or model prediction. We had some intelligent group of people. We thought we can explore the use of the AI to separate internal variability from the force response. With respect to the observation, yeah, our discussion were very much similar in the line, and that, yeah, we need to use more than one data product, particularly if you are using reanalysis. Yeah, make sure like, is it directly a simulated product or something that you need to verify using the more in situ based measurement. So that's all.
All right. Thank you very much to all of the groups for your valuable input. And we're going to transition now to our next session on Earth System Processes that's chaired by Isla.
All right, so this first session is about kind of fully coupled Earth system processes. So we've heard a lot about things like temperature and precipitation, and we're getting into other components of the Earth system where there's, I think, a lot of emerging things that we'll start to have to confront our models with observation. So we're going to kick things off with an invited talk by Sonia Seneviratne.
Yeah, so again, thank you for this invitation. As mentioned, I did include also a few slides, a bit on some other material, actually more generally on this question of confronting models with observation. And I would like to thank many people of our group who have contributed to publication I will be showing. So here is the outline of my presentation. First, I want to discuss some observational uncertainties. This is a topic that was discussed this week, but I just wanted to show some results which I think are interesting for droughts. And I also want to discuss some aspects of how you can separate some sources of biases. Then I'll discuss drought climate feedbacks about relevant processes, some evidence of differences between assessment models and observation, and also what are the potential impacts for the carbon cycle. And then I'll discuss a few open questions. So I want to start with this figure. This is from a paper from Martin Hirschi, which is currently in review in Hesse. And we looked in this paper at different trends of droughts based on a range of datasets, reanalysis products, and also satellite product. And one thing I wanted to highlight, and for this I would support very much, for instance, one of the previous speakers was saying about, for instance, evaluating uncertainty in products. It's not only about statistics, it's also about understanding the processes. So for instance, here, if you look at those trends, it's the trends in dry season soil moisture from 2000 to 2020. You have three different products. One is the ERA5 root zone soil moisture, and you have ERA5 land root zone and MERA2 root zone. Now, at first sight, if you compare those three different figures, it does look very different. So for instance, in Europe, in ERA5, there is quite a bit of a drying, while MERA is not really showing this. There is also substantial differences in Africa. So you see that in Central Africa, ERA5 and ERA5 land are showing a drying, while MERA2 is showing a wettening. So of course, there are large uncertainties in observational products. And I think it's really useful to try and understand what are the causes of those uncertainties, because in some cases, you might want to trust one product more than the other. So in this case, for instance, if you compare also the trends in precipitation, now I'm only focusing on ERA5 and MERA2 because ERA5 land is very similar to ERA5. So if we compare trends in precipitation here at the top in the two products and then trends in temperature, what you will see is that, for instance, over Europe, where we had the drying in ERA5, soil moisture, basically there is also a drying in precipitation. And it looks like this drying is closer to what has been actually observed. So if you take GBCC, precipitation observation, it seems to match better. Also, if you look, for instance, at temperature, which is an important driver for the droughts because of increasing evapotranspiration, actually, all three products show quite a trend towards higher temperatures in Europe. But for instance, in Central Africa, where we had this discrepancy in soil moisture, you see that ERA5 has high temperatures. And if you compare it to the Berkeley temperature dataset, it seems more or less consistent. Maybe there's more white spot. But in any case, the MERA2 temperature trends don't seem to really match what Berkeley is. So, I mean, of course, none of those comparisons are perfect. But I think, for instance, in this case, we came to the conclusion that probably we could trust less MERA2. And the reason is that if you look at how those reanalysis products are being produced, in MERA2, there is no assimilation of observed temperature to meet the temperature, while ERA5 is assimilated in this temperature. And other metrics we looked at suggested that ERA5 temperature was substantially better than MERA2. So just one example, and of course there would be other processes to compare, but in any case, when we are looking at this question of comparing a model simulation with some observation, I guess the question we have if we have those two evolution, one in a model simulation, one in observation. The question is this consistent? And I would suggest possibly three steps, among other aspects. One is to consider the observational spread, consider the model spread with several realization and looking, and for me that's really important. I think it was discussed a bit less in this introductory presentation this morning, the process-based evaluation of single components. And I say a few words about that. So again, about observational spread, you may have this type of spread. But again, if you look very carefully at some of those observational products, you might get rid actually of this observational product, which for some reason doesn't seem to be consistent, for instance, with some other sources of measurements. On the other hand, now, of course, we also want to look at the overall spread in models. So you might want to look at several model realization, as Clara has shown in her presentation on the first day. So obviously this is also important, the spread in model realizations. But we should be also aware maybe that this total spread might be a bit of an overestimate of the total spread that would be reasonable in some cases, because for instance, if you were to run simulations with atmospheric nudging, so you prescribe the wind circulation in the given climate models, and you find in the end that in this setup, the model is substantially different from the observation, then you could actually come to the conclusion that there are some fundamental thermodynamic biases in the model. I come back to this point. So I think it is, of course, useful to consider that if you look at the total spread of the model, maybe this allows to look at the different possible realizations, but there are also other ways to constrain the models. So here I want to show some experiments we did. It was a previous paper from Catherine Verley, and there we tried to disentangle basically the dynamic versus thermodynamic origin of climate model biases. And what we did, this was actually with the CSM 1.2 models, was to have on the one hand a simulation actually where we prescribe SST, but there was interactive atmosphere and land. And then we had a simulation where we nudge the winds. So basically we have prescribed wind circulation, which means that we assume that the dynamics is correct. Now, if you compare these as the mean biases compared to crew TS for temperature, you compare the biases for the 4 different seasons. For instance, in summer, we find this model tended to be much too hot. Now, if we prescribe the circulation patterns, it gets maybe a bit better, but you see that much of the bias remains. So in the end, it's not only a question of dynamics, there seems to be some essential thermodynamic basically bias in the model. So a larger fraction of the bias remain even if you prescribe dynamics, and this would be a way to test the model in a different setup. It would be, of course, the same with trends. So if you prescribe the circulation patterns, that would be corresponding to what has been observed, and you can compare the trends that are simulated in the model when they have the right dynamics with the actual trends that were found in the observation. This is another such analysis for extreme metrics. For instance, here you have the TX6, that's the hottest day of the year, or the TNN, that's the coldest night of the year. And you see that, again, here, the biases in the interactive atmosphere setup and the setup with nudge wind remain quite similar, so it suggests, again, the presence of substantial thermodynamic biases. I just wanted to mention there's been a recent paper we published in 2022 using a similar setup, but now including 3 different models. So we have a simulation at the same time with CSM and also ECRS and MyROG. And in those simulations, basically for the time frame 2009 to 2015, 2016, we have several setups, either fully interactive or then we prescribe, for instance, atmospheric winds, we prescribe SST, or we prescribe some moisture. And if people are interested in those simulations, you're welcome to contact me. And we also have some new simulations we are running at the moment with CSM 212 and ERA5 atmospheric winds. And again, there I'm happy to discuss more about this if you have any questions. Another point that was mentioned also, for instance, by Clara on the first day was the issue of forcing. And there, I think the people participating in the workshop, maybe not many of you are working with regional models, but it is important for projections which are used by policymakers to also look at those regional projections. And we found in a study that is led by Dominic Schumacher that the Cordex simulation in Europe have substantial biases compared to observations. So it was also already mentioned that it seems that there is a bit additional warming in Europe, West Central Europe, which is due to a change in dynamic component. And that's what you see here, that, for instance, if you look at ERA5 and the CMIP6 models, it seems the CMIP6 models are slightly underestimating the observed warming. But this issue is much bigger if you're looking at Cordex simulation, so there is an additional issue here. And what we found was this was related to the fact that most of the Cordex simulation only included constant aerosols. So actually for the total temperature trend that in that region, in West Central Europe, we find that, again, there is really a very large trend. And indeed, part of it was due to a dynamic component, but the largest part is due to thermodynamic, and that's a combination of greenhouse gas forcing and a decrease in aerosol forcing. So for instance, here, if you look at the Cordex simulations, you look at basically what has simulated change in temperature, the thermodynamic component as function of change in net radiation. Obviously, the simulations that have constant aerosol have much too little increase in net radiation. As a result, they have much too little increase in temperature, while those that have time-evolving aerosols have substantially more increase in radiation and temperature. But unfortunately, there are much less such simulations. And I think this is important to realize because, of course, there are also Cordex simulation in other regions. And again, the past set of Cordex simulation mostly included basically constant aerosols. So now I want to say a few words about dry climate feedbacks and about the relevant processes. In this context, I think a really important point is that, and that's some point that has been made in the last IPCC report, is that when we speak of droughts, we should not only look at changes in precipitation. Yeah, and so that actually for a lot of the impact, what matters is agricultural and ecological drought, so basically lack of soil moisture. And for this change in basically soil moisture, there are really two main drivers. On one hand, a lack of soil moisture, which can be related to the lack of precipitation, but actually to the larger part, actually to an increase in evapotranspiration. And also vapor pressure deficit can be an additional source of stress for vegetation. So here I'm showing a figure from the last IPCC report where we looked at observed trends in agricultural and ecological drought, so change in the water balance, also moisture. And I think I would encourage all of you who are interested in drought, so for instance, check the source of this data. So the figure, this is a figure and a summary for policymaker. It's based on tables we have in our chapters, chapter 11. And basically for all of those regions, we assessed from the literature if there was a consistency on observed trends towards, for instance, drying, and then also compared this with model simulations. And so all those regions here in yellow show from the observation and tendency towards drying. And then we have an attribution which is associated with a model signal. And so what you see is that the dominant signal from observations in several regions is drying, and there is a strong attributable signal in some regions, mostly in the Mediterranean and in Western North America. In some other regions, it's less clear, so where there is only one dot, we have actually limited confidence basically in the attribution. So a really important point is most of the signal is not associated to precipitation. So what we find is that human-induced component of this trend is due to increase in land evapotranspiration. So this means that any study trying to understand those trends needs to look at evapotranspiration. Again, for the underlying data for this figure, we have a lot of tables. These are pages 1613 to 1705, where we have this type of tables for different regions, where we basically assess changes in meteorological drought, agricultural drought, and hydrological drought. So we looked at basically the observed trends, the attribution, and also projections at different levels of global warming. And if you have any comments, of course, I'm very happy for input. I should say also we are working with colleagues on an update of those tables and of the figure. Now, I want just to mention that there seems to be some cases where the models don't seem totally to really match the observations. So for instance, we had a study about drought trends in West Central Europe because we had a very extensive drought in 2022. And from the observation, there seems to be a clear trend towards drying. So here you have a range of different data sets that shows this drying. Now, the models generally showed also a tendency towards drying. That's what is shown here, for instance, change in intensity or change in probability, but the overall signal tended to be much smaller, for instance, probability ratio much smaller than for the observation. So I don't have time to go into the detail, but quantitatively, it looks like the signal basically is underestimated in models. Now, that's just for one region, but I would like to point actually to a poster from ILA, which I think is really interesting and that is showing a discrepancy in atmospheric drying in different regions of the world. I would encourage many of you to check it. It's a question I have for me right now, whether some of this discrepancy we see, for instance, in Europe, is associated also with other discrepancy elsewhere. And there is also a relevant paper from Herve Douville and Piazzotta from 2017 that shows something goes in a similar direction. So I will finish just with potential for global feedbacks from the change in droughts and the uncertainty in drought projections. I'm sorry, there is a lot of text here, but the point I wanted to make is that's from IPCC figure here, showing the change in global mean warming as function of cumulative CO2, and this is from an early paper we had where we looked at change in hot extremes as function of global warming. In both cases, you see those relationships seems to be very linear. So the models behave very linearly, and so far it seems more or less consistent with observations. But I do wonder if there is potential for tipping points, again, if some of those changes are underestimated. In particular, related to droughts, I would say one hotspot is the Amazon rainforest, because there is potential feedback from Amazon dieback on the global carbon cycle. And for instance, here, this estimate of global tipping point has come to assessment that this tipping point would only be reached between about 2 degrees and 4 degrees of global warming. Question that is for me open is whether this might be too optimistic. For instance, if we have droughts happening a bit more quickly in these regions. So we had a study based on observation where we looked at the variations in terrestrial water storage on land from satellite data, that's a gray satellite, and then the CO2 growth rate in the atmosphere. I don't have time to discuss the details, but I think what you see right away is those time series seems to be very correlated. And the explanation for this is most likely that basically when you have more droughts, vegetation has I have more problem basically to take up CO2. You also have maybe more release of CO2 if plants die or if there are fires. So I just want to point to some results which for me are a bit disturbing. It's a recent study led by Labao Liu in our group. And here we look at this correlation between tropical water variations and the interannual CO2 growth rate variations. And what we found was in observation, first in observation we found there is strong correlation. And what we find is also that that's a difference between two time periods, that recently this correlation has become more negative. This suggests a stronger limitation of CO2 uptake by plants in recent years compared to the past. Now, actually, the models, both the coupled models and offline models, don't seem to capture this change in correlation. This means that they might be underestimating the impact of droughts on the global carbon cycle. So I'll skip this because I'm running late, but I think this impact of droughts on the carbon cycle, actually other processes on carbon cycle, is really a major issue. It's also not only relevant in the context of drought climate feedback, but also in the context, for instance, of afforestation, speaking about possible solutions to human-induced climate change. For instance, in the context of afforestation, Felix Jäger is now visiting NCAR for a few months, and he has also a poster, so I recommend you to check it. And one thing that we found is a study led by Felix is basically that a lot of the regions where forests basically plan to be planted to take up CO2 in low emission scenario, they tend to be affected by stronger risk of fires than in the past. So I come to some open questions. First, the drought relevance for record-shattering heat wave. Of course, this question of to which extent we can have really record-shattering events is really important. And we do know that some moisture temperature feedback can be very relevant for this. There's been a lot of publications on this, but I wanted to highlight these recent results from Dominique Schumacher, published in Earth's Future, where we look at the Pacific Northwest heat wave. And you see here the total anomaly of this heat wave, and here the contribution of some moisture anomaly at the beginning of the event to the total heat wave. And so the heat wave anomaly was up to about 20 degrees Celsius, and about 1/4 of this, 5 degrees, was due to some moisture feedback because you started basically event with dry conditions. Now for the future, of course, the question is if we have more droughts than expected, this could also mean much more heat waves. Last point I wanted to mention, it's really just work in progress from a student in our group, Svenja Seber, You were interested in the recent few months, which were really very extreme, and for me, do question whether the models do a good enough job. So for instance, here you look at the anomaly of September 2023, very high temperatures, actually also very strong temperatures in Europe. And we looked, what Svenja looked at was to which extent this event, so the global mean anomaly, was consistent with what the global simulations or system models are simulating. Alone from the observation, it seems to be a total outlier. From the models, this event seems still to be more or less included in the total range, but still it's very much at the limit of what the model is simulating, and I think that's something we need to continue to monitor. Interestingly, it doesn't seem that the event is better captured by the so-called hot models of SEMI6 than those that are, basically don't have a very strong climate sensitivity. So I come to the conclusion. Confronting a system model with observation requires consideration of several dimensions: the observational uncertainty, internal climate variability in our system models, and isolating the sources of bias. So I think really looking into the processes is essential as well, for instance, with factorial experiments. And there seems to be biases in representation of drought climate feedbacks in Earth system models, if anything, rather an underestimation of the drought trends that have been observed. These have also important implications for the attribution and projection of droughts, but also for projection of heat waves and the global carbon cycle. And we need to basically better understand the underlying causes. And I'll say a personal question I have is whether the latest observation we have had in late 2023 and early in this year are consistent with the system models. Thanks for the attention.
Great. Okay, thank you. Yeah, so my name's Dave Lawrence. I'm from NCAR, and just a bit of context about me before I get started, because I think it raises an interesting point, is that most of my career I've spent being a model developer of the community land model and the community air system model. And I don't think many people in this room are model developers. I'm not totally sure. I don't know everyone. But it is interesting to think about all the problems we're identifying in this workshop, whether it feeds back into the modeling centers, whether we can do anything about it, right? So it's one thing to say the models aren't doing things well. It's another thing to try to make them do something better. So you'll see something in this talk where I'm trying to make the model better, how we're trying to do it in particular for this land problem. The carbon cycle on land. So just Sonia mentioned it a bit, but basically we haven't heard about the carbon cycle at all. So just to orient people, this is a canonical figure that I'm sure you've all seen in your Climate 101 about the historical emissions and the impact on the atmospheric CO2 burden. So obviously we've had fossil fuel emissions that have been rising through time. There's also been net carbon emissions from land due to land use change. And then fortunately the land and the ocean have been sinks of carbon. Some of that carbon has been emitted, and what was remaining is in the atmosphere. And about 45% roughly, more or less, of the carbon that's been emitted stays in the atmosphere, and about 55% is taken up by the land and ocean about equally. So that's a very brief primer on the carbon cycle. Here's what we're looking at in terms of the land. So this is a plot that we take from the International Land Model Benchmarking Package, which is trying to assess the land carbon stock, accumulated land carbon fluxes through the historical period. And so the gray bars there is an observational estimate of what the land carbon trend has been over the historical period, and then all the colored lines are the models. And what you'll see is, generally the land was losing carbon early in the record. That's due to land use change mainly, and then it's been gaining carbon over the most recent period, largely due to CO2 and nitrogen fertilization, and some climate change impacts probably. And what's interesting here is that the models, many of the models, almost all the models except for one, are getting to the right answer, roughly. They're within the observational uncertainty by the end of the record, but they're getting there in quite different pathways. That's one thing to point out. The second thing to point out here, and that one model that's way off, it's probably a data problem that they're not actually reporting the right thing for this particular field. But so one thing that's interesting is all these models are getting there, and you wonder why is that, getting in the right place was for the wrong reason. It's probably because these models are used in emissions-driven simulations. I'll make 2 points here. One is I want to say the observations are not actually observations. So they come from they're residual of the fossil fuel emissions. So there should be a minus sign, minus the change in the atmospheric concentration, minus the change in the ocean carbon, which is a model result. So this is not an observation. We're treating it as an observation, so keep that in mind. But why are the models all kind of getting the right answer, but getting there by different reasons? It's the same kind of thing as why we have the right temperature change over the historical record, even though the models are all doing different things. a modeling group is not going to release a model unless it gets a reasonable 20th century. That's just the way it works. So we're kind of forcing that in here. We also aren't going to release the model unless we get a reasonable carbon cycle, because otherwise we can't do emissions-driven simulations and come up with a reasonable CO2 by the end of the simulation. So all the models are producing something reasonable in terms of atmospheric CO2. The OBS by the end of this record are 400 ppm, and the models are getting 405 plus or minus 15 ppm. It's right in the right range. It does introduce additional uncertainty to the total climate change, about a 30-40% increase in the range of simulated climate change over the historical period by having the emissions-driven simulations, but it's still within reasonable observational uncertainty. But then going to the future, the problem is that all the models are getting there to that same spot roughly, but they're all getting there for different reasons. And then, of course, as you would anticipate, if you got in the future, they start to really diverge, and so they get to very widely different levels. And so this is showing the total CO2 concentration in the atmosphere in these emissions-driven simulations for the SSP 585. What you see is that, relatively small range in the historical period of maybe 40, 45 ppm explodes up to 230 ppm by the end of the 21st century for this, extreme climate change scenario. And that's a big uncertainty in the overall climate change. It's about 1.2 degrees Celsius on the 3.7 degrees Celsius mean change. So this is not an unimportant feature of the system. And it's becoming even more important going into CMF7 as basically everyone around the world has decided that we should probably be transitioning to emissions-driven simulations as what we do by default if we possibly can, because these feedbacks are really important and we're not really, properly assessing them in our system models routinely. Okay, and then the other motivation here is, I'm not going to dwell on it, is just, if you're trying to go to mitigation, where are we going to put the carbon? You need to use land-based strategies like reforestation and BECCS, to get there, and many other things like reducing emissions. And if we don't have good carbon cycles in our model, then anything we're trying to say about this is probably not trusted. Okay, so what drives the land carbon stock trajectory? It's due to several things. So as I mentioned at the right at the beginning, the first part of the record especially, it was dominated by the land use change signal before the CO2 in the atmosphere had risen. And this is a zonal mean plot of what it looks like. It's basically land use change happening around the world, accumulated over the whole record, is leading to a loss of carbon on land. Then as the CO2 increases in the atmosphere, and plants really like that CO2, they tend to grow more carbon, they tend to drop more litter. That litter gets into the soils and gets stored either in wood or in soil carbon. Has been largely a sink due to that CO2 and also some nutrient fertilization from nitrogen deposition. So that's been a sink. And these two actually balance each other out over the historical record, coincidentally, really, to the point that the land has basically been a net zero over the historical record. In land-only simulations, we can sort of try to diagnose where this is coming from, or what's driving these factors, what's driving the land carbon stock trajectory. So you can run simulations where you just do land use change, or you just increase CO2 or nitrogen deposition, or you just change climate. And this is land-only simulations. And what you see is that exactly this, that there's a sink of carbon due to the increase in CO2 and nitrogen deposition. There's a loss of carbon due to land use change in both the vegetation and the soil carbon. And actually, the climate change impact is relatively neutral over the historical record in land-only simulations. And the net is slightly a sink, because in this case, we've gone out a little bit further into 2020 when it's starting to become a sink. So there's all these different things that are affecting it. There's the land use change, which is related to a bunch of things: deforestation, agriculture, wood harvest. Then there's the fertilization of plants by CO2 and nitrogen. Then there's vegetation and soil carbon response to climate change and variability. And really everything is determined in the models by the effective residence time of carbon in these different pools, which is controlled by a bunch of different factors, biotic and abiotic factors like climate. And this is just sort of showing this sort of separating the CO2 effect from the climate effect, and just sort of illustrating why the CO2 effect is showing up as a strong signal. So everywhere in land, you're gaining carbon due to the CO2 fertilization effect, but the climate effect is really mixed. Like Sonia indicated, climate can affect the carbon fluxes on land and carbon stocks on land, but it's really mixed across the globe. And if you average across the globe, it ends up being close to zero over the historical period, at least in land-only simulations. Okay, so there's the way I look at it and started trying to understand this problem. There's two pretty big challenges. One is that, all models are missing some relevant processes that would be important to the overall carbon cycle. And I think that's interesting to think about this relative to a lot of the things we've heard about this week, where we're looking at changes in extremes or changes in circulation, changes in precipitation. no one's been saying in this room saying, well, we don't have enough physics in the model to be able to capture these things. That's why the models are wrong. Or the physics may not be sufficiently good, or there may be something you don't understand about the physics, but there's not a big saying like, modelers are dumb, you forgot process X. On the land, you can't really say that. There are modelers are dumb, in quotes. We haven't included all the processes. Only a fraction of the models actually representing wood harvest. Almost no models representing shifting cultivation. No models essentially representing agricultural management. About half the CMIP6 models are representing the effect of nutrients. Only one model is representing permafrost carbon processes. 30% of the models representing fire. No models are representing lateral carbon flow. So we don't have a comprehensive representation of the land carbon flux systems. That does make analyzing these models against observations more challenging. And the other point I want to make here is that the observed land carbon stock, make it again, is actually not an observation. Gavin pointed this out, that nothing we're looking at is really an observation. All satellite observations are gone through some model, but in this case it's like 100% a model product. So are there other observational trends that we can use? I'll get to that here. And I just want to say, I think if you're going to, models are kind of trying to pick off these things one by one. All the different centers are adding these features, and some models have more representation than others. And I think, in my opinion, the most important is wood harvest, nutrients, and fire. If you're going to take on, ones to pick off, and most models are kind of getting to that point. In CMF7, probably most models will have that. Okay, so what can we do if we don't have good observations and the models are incomplete? I'm not going to really get to the models incomplete part, but okay, what do we have? Well, we do have the atmospheric CO2 records. That's kind of a nice constraint. And it's combined impact from the ocean and the land, but on land, if we assume a lot of the variability is coming from land, you can sort of look at the different epochs of the historical record and ask whether or not the models are reasonably reproducing the CO2 trend in the atmosphere in emissions-driven simulations. What you see is that for most of these eras, it's doing okay, but this one era, era 3, all models are way off. They're all producing a trend that's overestimated by about 5 ppmv per that 2-decade period. And so why? So there's a bunch of hypotheses about that, but this is kind of giving an, maybe it's the CO2 emissions are incorrect. It was World War II. The whole world was in a weird place in that time. So maybe something related to that. It could be internal variability. Could be that it's missing some land use change and land abandonment. So that's interesting to try to understand better. I'm going to skip over this point on using ecosystem manipulation experiments to test your models. It's not really a carbon trend thing, but it is an interesting way to evaluate models using ecosystem model experiments. In the interest of time, I want to have a few minutes here to talk about our recent work. And so then, what can we do? Well, fortunately, there are, the records are now getting long enough from satellites and from tower sites that we can actually start seeing trends, observing trends in the real world. And so this is an example on the left showing the live woody biomass trend estimates from a combination of forest inventory and satellite estimates through some machine learning algorithms. And what you can see here is, different trends across the world in terms of the amount of carbon that is stored in vegetation on land. So that's actually a product that we can potentially use to confront our models now, a real observational, quote-unquote, observational product. There's also leaf area index greening and browning trends. There's local and upscaled estimates of carbon flux trends from these long-term flux tower sites. There's about 200 flux tower sites around the world that have been doing long-term monitoring, and maybe about a dozen of those have records that are extending out to 20 years or so. Okay, so what we've been doing in the last couple of years here is looking at our model, the community land model, which does have a relatively rich process representation. There's not too many items on that list of missing processes that we don't have. There are some, but we think we have the most of the important ones. And then asking, okay, what's going on? We know that these models are extremely parameter heavy. CLM has over 200 parameters in it. And most of those parameters we don't have good observational constraints on. So there's huge uncertainty coming from our understanding of the parameters. So this plot is probably not that exciting to many people, but it's extremely exciting to us, is that we can actually now run historical carbon simulations, large ensembles of them, about 500. And the reason that's been hard before is that it takes really long time periods to spin up these models. It takes, in CLM, it used to take about 1,000 years. And so it's prohibitively expensive to run an ensemble of simulations. We've gotten that down to about 140 years to spin up. We've also found a way to run a sparse grid so we can run these large ensembles. So we've run this Latin hypercube generated set of ensemble members for the historical period. And what you see here is a relatively wide range in that, but not too bad. It's not too bad over the historical period. And of course, as you go out into the future, it blows up. And in fact, the range is nearly as large as it is across the entire CMIP6 archive, just from the one model that we have, CLM. So a spread of 574 petagrams of carbon, convert that straight into ppm in the atmosphere, that's about 200, 250 ppm if all that carbon stayed in the atmosphere. Okay, so this is obviously a problem. So what can we do about it? So then are there any observational constraints we can use to try to constrain the model? So we've been trying to use some of these observational constraints and saying, okay, let's throw out the parameter sets that don't meet some observational constraints. And I'll say this is very, very preliminary work. We're just sort of hypothetically thinking about whether or not this will possibly work without spending too much time on all the details. So let's just say, let's throw out all the parameter sets that don't have a leaf area indexes within a reasonable mean and a reasonable trend. Throw out everything that doesn't have a reasonable total land use flux. Throw out everything that doesn't have recent historical carbon sink trend based on that work from the total live biomass trends. Okay, so here's what happens if we use the LAI constraint. You see, actually, it didn't help too much. We still have this pretty wide range, so it didn't do much in terms of constraining it. Here's when you add the total land use flux constraint. There's observational, sort of quasi-observational estimates from these so-called bookkeeping models. That also doesn't provide much constraint. But if we actually add in the recent historical sink constraint from that live woody biomass, we're starting to see that we actually are constraining the model. And then, the spread is now down to about 250 petagrams, 270 petagrams, and we see a smaller net sink on land in this SSP37. So looks like there's some promise that we might be able to use this to start constraining our models. And I'll just say, we're definitely thinking very strongly about moving away from having a parameter set for CLM and actually having about, giving the community 50, 200, 1,000 potentially plausible parameter sets that they can then use to explore the system and hopefully get to the point where we're running at least a handful of those parameter sets in the fully coupled Earth system model to start sampling that parameter uncertainty from land, and then you could do the same thing in the atmosphere and the ocean. So I'll stop there and put up my summary slide, which is really not super exciting. So I think since I'm at time, I will not read through it. Thank you.
So hi everyone, I'm Olivia Clifton. I'm at NASA GISS and Columbia. And today I'm going to be talking about air pollution and internal climate variability. So air pollution is a leading cause of premature mortality globally. In particular, PM 2.5 is a leading cause of premature mortality. So PM 2.5 is particulate matter with a diameter of 2.5 micrometers or less. That's important because small particles can get deep in your lungs and be harmful to you. And so because this is a climate crowd, I'll just say that PM is synonymous with aerosols. So PM 2.5 is made up of a bunch of different constituents. We have sulfate, ammonium, nitrate, organic aerosol, black carbon, and composition varies by location and season. Different PM types have different sources. Some are overlapping. Some sources are natural and highly tied to climate. Others are anthropogenic. And so particles can be directly emitted to the atmosphere or formed in the atmosphere after oxidation of precursor gases. And then there's a bunch of processing that happens in the atmosphere. Particles can get transported around and then removed by precipitation. So that's wet deposition, or turbulence can transfer particles to the surface and then they just stick to the surface. That's dry deposition. So there have been large regionally distinct changes in PM 2.5 over the past few decades, and this corresponds mostly to changes in anthropogenic emissions. So here we're looking at trends in satellite-based PM 2.5 over 1998 to 2018. So we can see over the US and Europe, we have decreases in PM 2.5, whereas over India and northern China, we have increases. Then on the right-hand side, we're looking at the average across ground-based monitoring stations in CONUS over 2000 to 2022. We see this steep decline in PM 2.5 up until about 2015. That's reductions in precursor emission controls. And then we see a lot of interannual variability in more recent years and perhaps an increasing trend. And that's thought to be due to wildfires. And so I won't get into wildfires today, but it's an important component of the relationship between climate variability and PM 2.5 that I think my work will at least set the stage for examining this later. So we rely on observational records of PM to estimate the efficiency of anthropogenic emission controls and advanced process understanding of PM. And I don't really have to harp to this audience much that internal climate variability is going to matter there much, but for atmospheric chemistry and air quality, this idea hasn't received too much attention. So this is a figure from a perspective piece by Ruth Doherty a couple of years ago, where she talks about, in terms of air pollution and climate change, we've thought a lot about future scenario uncertainty and model structural uncertainty, but we've tended to overlook uncertainty in internal climate variability. So the goal of this work is to understand the extent to which observed PM2.5 trends are imprinted by climate variability. So in particular, I'm looking at historical CMIP6 simulations with interactive aerosols, mostly looking at GIS E2.1, for which we have two aerosol configurations, OMA and matrix. OMA is more simplified, matrix is more complex. And for each of these aerosol configurations, we have 10 ensemble members each. So that's really cool. And then I've also recently added in CSM2 to this analysis. There's 3 ensemble members in the CMIP archive, so I'm looking at those, but Arlene Fiore has recently expanded this to 12, and so I hope to work that into my analysis. So I'm not going to address this overarching goal, just address some first steps so far that I've done. The first of which is to establish whether this set of simulations captures observed PM trends as well as the observed range of interannual variability. And I'll talk about why I have observed in quotation marks, but I think you probably know in a second, and then use this analysis to uncover model strengths and limitations. So few places have long-term ground-based observations of PM, most places have none, or they've just started records in recent years, but we do have over 2 decades of satellite retrievals of quantities like aerosol optical depth, or AOD, that can be linked to near-surface PM. So here I'm going to be looking at a global monthly PM2.5 product that includes uncertainty estimates. I haven't yet incorporated those uncertainty estimates into my analysis, but plan to shortly. And it's from 1998 onwards, and it was developed by Van Donkler et al. So it combines satellite retrievals of AOD, chemical transport modeling, and ground-based measurements. And so this is a snapshot of what the product looks like from January 2018. And then the little dots on this map are where there are ground-based station measurements and where they've informed the product. And so we can see that there are a lot of station measurements over the US, over Europe, and over India and China. So India and China measurements have started more recently. The US and Europe are more long-term. And so for now, I'm going to focus on the US and also think about an observation product that's just based on the ground-based observations in the US. So the stations in the US that have been measuring PM2.5 for a long time are the stations that are used for assessment with the National Ambient Air Quality Standards. So they're population-based, so you can see that in places with a lot of people, there are monitors. In places where there are not a lot of people, there are not monitors. And so I use a gridded product of PM2.5 as monthly averages from this data set. And I only have kind of a decade worth of this product so far, or I've only incorporated a decade of this product into my analysis so far, but I've recently received the product from 1998 to more recent years. So I'll just be using this product to kind of sanity check the satellite-based product. And so I'm going to look at 6 different regions in the US, the Northeast, the Southeast, Midwest, Central US, Intermountainous West, and Northwest. So here we're looking at annual PM2.5 over these regions from 98 to 2014. So 98 is when the satellite product started. 2014 is the end of our historical simulations. And we can see OMA and matrix, those are the different aerosol configurations of E2.1 and CSM. So the thick lines are the ensemble averages and the thin lines are the individual ensemble members. So we see some interesting model differences, similarities. One thing I'll point out is this like coherent interannual variability in the Western US. That's due to forced biomass burning emissions. And those biomass burning emissions in the satellite era have been informed by aerosol AOD. And so this interannual variability is going to match up really well with the satellite product when I show that later on. Okay, so here now I'm showing the satellite product and the ground-based product in the dashed and solid lines. We can see that for the eastern US, the Midwest, where we have a lot of ground-based stations, the products match up pretty well in terms of interannual variability and magnitude, although there are some differences. But then in the central US and the Intermountainous West, they don't look so similar. And that makes sense because there's not a lot of ground-based sites there, so the satellite-based product is making a lot of assumptions. We can also see that the models are pretty low in terms of PM 2.5 relative to these observation-based products. I'm more interested in trends and interannual variability here, but of course these, as we've been talking about, these kind of mean state biases might influence our findings with regards to trends and interannual variability. Here we're looking at annual anomalies in PM 2.5 for the models and the satellite product. So if you just ignore the trends right now, it seems like the models are capturing the range of interannual variability pretty well. Here we're looking at the trends. So the different rows are the different regions, the black dots are the satellite-based product, and then the colors are the model with the range as the range across the different ensemble members. And we can see that the models are slightly overestimating these really small trends in the Western and Central US. Matrix is capturing what's happening in the Midwest pretty well, or what's happening as suggested by the satellite-based product. The other models are slightly underestimating it, whereas in the Eastern US, the models are pretty low compared to the satellite-based decreasing trends. If we break things up by season, we can learn a lot. So here we're looking at wintertime and summer. Looks like for the Western US in winter, the models are capturing the satellite-based product pretty well, but then there's something going on in the Central US, Midwest, Southeast, and Northeast, and I'll get into that in the next slide. Then in summer, what stands out to me most is what's happening in the Southeast US, where there's large range across the different models, as well as the different ensemble members, especially for CSM2, and they're really not capturing what the satellites suggest. So I'll get into that in 2 slides. So what's happening during winter over the Eastern, Midwest, and Central US? And I'll just say to start, satellite-based product is pretty uncertain during winter because we have a lot of clouds, but I still think we can learn something here. So I'll start with the Central US, where CSM2 is really capturing what the satellite suggests, whereas E2.1 is overestimating the decreasing trend. If we look at the different species, we can see that it's basically an ammonium nitrate sulfate story. So I'll just say that there's a lot of nonlinear aerosol thermodynamics in what's going on here. But basically in E2.1, we have decreases in ammonium, nitrate, and sulfate that are mostly driven by nitrate that are driving the strong decreasing trends. CSM2 does not have nitrate, so it does not get as strong of a trend as E2.1, and it also has no change in ammonium, which is different from Model E. So then what's happening for the Midwest, Southeast, and the Northeast is all the same, so I'm just going to show what's happening for the Northeast. In the Northeast, it's really a nitrate and sulfate story, where nitrate is increasing in E2.1, but sulfate is decreasing. Again, CSM2 does not have nitrate, so it doesn't have this offsetting that is present in E2.1. And then interestingly, the sulfate increase in CSM2 is much weaker than in E2.1. So it's hard to assess what's going on here, whether the models are getting the breakdown of the different species correctly, but luckily we have ground-based nitrate and sulfate measurements since the late 1990s at some sites across the US. And so my next step will be to evaluate with this data. And again, I think that'll be really useful just because the wintertime satellite-based product is so uncertain. Okay, and so then the second case study is what's going on during summer over the southeastern US. So I'll just remind everyone that the southeast US has a lot of trees. Climate influences the trees. The trees in the southeast emit a lot of volatile organic compounds, isoprene and monoterpenes that undergo chemistry to produce secondary organic aerosol. So the fact that there was a lot of uncertainty in the southeast, especially during summer, when these compounds are being emitted from the trees, made me immediately first think that, okay, what's happening is having to do with organic aerosol. And so we see this really large range across the different ensemble members for CSM2, and there's only 3 ensemble members for CSM2. And so if I take out organic aerosol from this trend, we see that the range across the ensemble members is much weaker, and we have a stronger decreasing trend. And so if we look at what's happening to organic aerosol across the models, we see that we have an increase in CSM2, but we have a decrease in OMA and no change in matrix. And the lack of variability in matrix is due to very much so oversimplified secondary organic aerosol formation chemistry. And so, again, luckily we have these ground-based organic aerosol measurements over the southeast over the past couple of decades, which do show decreases. So I'm not quite sure what's going on in CSM2 here, but my next step will be to use these measurements to further parse out what's happening. Okay, so the takeaways from this work. The ugly is that PM 2.5 observational products are really imperfect and uncertain and rather short term. The bad is that representation of nitrate, sulfate, and secondary organic aerosol probably needs to be scrutinized in the models. The bad and good is that models are too low in terms of PM 2.5, but they generally capture interannual variability and trends. I think that the models were performing a bit better than I anticipated. The good is that I think we can still learn from these model observation comparisons, especially when we break things down by season and species and think about model structural uncertainty as well as internal variability, even if these observational products are imperfect. And the good may be that we're able to use these tools to understand the extent to which observed PM 2.5 trends are imprinted by climate variability.
Thank you. Hi, everyone. It's a pleasure for me to be with you today. And I would like to thank the organizers for giving me the opportunity to present remotely some recent studies, suggesting that it may be both urgent and possible to constrain global projections of water cycle changes, at least as soon as we have reliable enough multi-decadal observations. And it's not always the case in the illustrations that I will present today. First of all, I would like to emphasize the fact that the water cycle is not a passive component of the global Earth system, as it was suggested, for instance, by Sonia in a previous talk. It's fully interactive with both the energy and carbon cycle. So it's not only a question of adaptation, it's also a potential issue for mitigation. And in fact, all the SSP scenarios that are relevant, at least that are suitable or compatible with the Paris Agreement, won't be possible if we don't have enough water resources over land. So as already emphasized by many speakers, the quantification of the forced response to anthropogenic forcing in the observations is one of the burning questions of this workshop. And it has given rise to the development of powerful detection and attribution methods, But another key question is probably to quantify what are the implications for climate projections. And with the growing emergence of climate change in the instrumental record, climate models are no longer black boxes. For the first time in the IPCC history, the projections of global warming have been assessed by combining multimodal projections with observational constraints in the latest assessment report. But it was argued by the IPCC that such methods do not yet exist or are not robust enough for many other variables, including those related to the water cycle, thus leading to potential inconsistencies between the constraint projection of global warming and the unconstrained projections of precipitation, for instance. This issue was also emphasized by Hausfather and colleagues, who suggested that the ensemble mean of SEMIP6 model should not be used as we had done before with the previous model generations because of the hot model problem. And but they did not really propose a real solution other than finding other metrics, more relevant metrics when the model spread is not clearly related to the spread in climate sensitivity. And this has led a few of us, of the previous IPCC IR6 co-authors of Chapter 8 to emphasize that water remains a blind spot in climate change policy. Faced with this persistent situation, more and more studies have moved from a conventional evaluation of individual models to the development of emergent constraints that link modeling uncertainty in projections to an observable metric across a model ensemble, but with two potential major drawbacks. As it was maybe suggested by Dave Lawrence earlier, a growing dichotomy between model developers and model users, and also the proliferation of probably overconfident projections, since most emergent constraints rely on a linear regression empirical framework, where potential outliers have a major influence on the results, and where in fact the proposed metrics or constraint, emergent constraint, are rarely reproducible from one model generation to the next. So in order to overcome the latter difficulty, a more robust and straightforward method has been recently developed at CNRM by Aurélien Ribes and Saïd Kasmi. It was used during the IR6 for constraining global warming, and it is based on Bayesian statistics, and it uses the full historical record for one or two variables, not just a scalar metric, to constrain the projections. So I won't have time to explain the method, but I can say that it accounts for both modeling uncertainty and observational uncertainty when available, including internal variability. And the main assumption is that the truth is somewhere within the theoretical prior model distribution, which is generally calculated using a Gaussian distribution estimated from the ensemble mean and the ensemble spread, and then a posterior distribution of the forced model response is derived from the prior distribution and from the forced response estimated from the observations. So as a first example, I would like to illustrate the method looking at the annual runoff projection, SEMIP6 projection here at the outlet of the Ganges River, and constrained by an observational product that is a reconstruction using a land surface model, hydrological model, constrained by river discharge observations, which has been produced at ETH. So as you can see, the black dot represents annual mean observed anomalies from this Giron reconstruction in millimeter per day. And you can see also two solid lines that represent the forced ensemble mean model response using the full historical and here high emission scenario until the end of the 21st century, and before and after constraining the simulation with the reconstruction. So beyond a shift in the ensemble mean response, the method is expected to narrow the modeling uncertainty, here represented by shadings, which correspond here to the 595 confidence interval of the prior and posterior distribution. And in this case, the narrowing is of course limited because of the strong interannual variability in the observations and a low signal-to-noise ratio. But we can argue that each additional decade of observation will allow the method to further constrain the projection at a rate likely much faster than model improvement has been doing so far. If now you look at the same method applied to precipitation average over the Ganges River, using this time GPCC observation, you have exactly a similar result, that is a limited constraint, even if a recent decrease in precipitation suggests that the models that show the strongest increase in precipitation are not the most reliable, in line maybe with the fact that the models that show the strongest global warming and maybe also the strongest monsoon precipitation increase over South Asia are not the ones that we should trust. But again, what may be more interesting is to increase the signal to noise ratio, but looking at the ratio, at the annual runoff ratio, namely the ratio between the annual runoff and the annual precipitation average across the Ganges River basin. And this is the right panel where you have a lower variability, year-to-year variability, and a stronger signal to noise ratio, suggesting that some model overestimate the increase in this runoff ratio average over the Ganges River. So, of course, most SEMIP6 models, they do not account for water withdrawal, which may contribute to a decrease in runoff despite no increase in precipitation, no decrease in precipitation, sorry. But we find this behavior over many tropical rivers, including the Niger River, for instance. And so it's an open question to know if the mismatch between model and recent observation is mostly due to irrigation and water withdrawal, or as another potential reason, for instance, poor physical processes represented in the climate models. So my second example is about the global ocean water cycle. And it's about the well-known relationship on the left panel between the contrast in E minus P and the contrast in sea surface salinity over the global ocean when you distinguish salty from fresh water, using here, for instance, a median salinity threshold, as was done so far by Chang et al. Based on a new salinity dataset from the Institute of Atmospheric Physics in China, AAP. For this multimodal relationship, you can also use another way to define the two ocean subdomains. Instead of using a salinity threshold, which is more or less arbitrary, you can use the E equal P equal P, so the zero moisture convergence isoline. So in the observation using the RFI reanalysis, and in the model using each monthly fields from the corresponding model. So it's not a static definition, it's a dynamic definition, because here the two subdomains are defined based on the month-by-month variation of this isoline, not the climatology. And if you do that, you can so compute a global sea surface salinity contrast. And so I illustrate here the application of KCC first on global warming on the left panel using so the Acrut 5 observation from the mid-19th century up to 2022. And on the right panel, I also constrain the global salinity contrast using the same temperature observations. This is the reason why on the right panels, the observations are shown in gray, because these are the IAP salinity contrast observation, and they are not used here for the constraint. And you can see that it illustrates my former point, that is the fact that global warming, the historical global warming, does not constrain the water cycle, including over the global ocean, because you don't have any significant narrowing of the prior model distribution once you apply the constraint. When you apply the IAP dataset constraint on the salinity contrast simulated by the SEMIP6 model, you do obtain a downward shift of the whole distribution, but with a limited narrowing. And this is just slightly improved when you combine the two observational constraints, both from Acrut and AAP. But again, you can argue that even when considering that the later observations are perfect, you have a limited narrowing of the distribution, suggesting that we will have to wait for more decades of observation to decide which are the poorest models. Another interesting point is that if you distinguish the two subdomains, you challenge the well-known salty get saltier, fresh get fresher paradigm, which was already challenged over land with the fact that the wet get wetter, dry get drier paradigm is an oversimplification of what is going on over land. But even over the ocean, it's not so obvious that if you look at the salty waters, at least at the domain where evaporation exceeds precipitation, you have a clear strengthening of this pattern. So moving to the last illustration, I will maybe skip this slide that basically illustrates the fact that the global warming is occurring at fairly constant, near constant tropospheric relative humidity in both models and observation. And here I have used GNSS reconstruction of total precipitable water over a limited period, but which are perfectly consistent with the model behavior over those limited decades. And I will move to the decrease in global land surface humidity, as has been already emphasized in some breakout group, I guess, and in a recent paper by Ayla. And instead of looking just at the dry land regions, I'm looking here at the global land surface. And I show that if you constrain, so the land surface relative humidity projected by those SEMIP6 model with global warming, you shift upward the distribution. While if you constrain then with the AD-ESDH observation, from Kate Whistlet, which have been recently updated until 2022 and which starts in 1973, you see that you have the opposite behavior. So it's not only the fact that global warming does not exert a strong constraint, it's also the fact that if the relationship between global warming and other variable or regional responses is not correct, you will in fact maybe deteriorate the projection by constraining them with global warming only. And so if you combine the two observational constraints, you do not change too much the ensemble mean response, but you exclude the possibility that there is not an overall drying of the land surface in this high mitigation scenario. And you can see that the recent trends are even stronger than the models that show the most consistent response with the observation. And it leads me to the final or almost final slide, where instead of trying to have a narrative such a hot model narrative as in the IR6, which in fact is a very unlikely narrative, a more likely narrative is a strong drying storyline. And here I show the difference between the top 10 SEMIP6 model that show the most realistic recent drying compared to the observation versus all SEMIP6 models. So you see that they have a stronger warming not only over Amazonia, but over the northern mid-latitude, and this is even more true if you focus on the summer seasons. And associated with this further drying, you do have a further warming over these areas. So even if the hot models are probably not reliable, in fact, you can argue, looking at the more realistic strong drying storylines, that the majority of SEMIP6 model may still underestimate the warming over land. And you can see that associated with that, you also have an extra warming over the ocean. So to conclude, I would like to repeat that global warming levels don't tell so much about water cycle changes. And in fact, Bayesian statistical methods such as CACC and alternative metrics are thus potentially useful to constrain the projections with, however, three contrasted situations. Good situations where all models are wrong, but some are useful, in line with the CACC assumption that models cannot be distinguished from the truth. A bad situation that has not been so much discussed so far, as I can think based on my morning participation to the workshop, the fact that if all models are tuned, we won't be able to apply KCC and the most emergent constraints because it won't be possible or suitable. And finally, the worst situation, the ugly situation, is that all models are wrong and maybe none are useful. And several presentations during those last 3 days, including mine, suggest that this ugly situation may not be an exception. So it raises the question of whether or not we should call into question the way the IPCC has so far informed decision makers. So thanks for your attention. I will be pleased to answer your questions in a few minutes, at least if you speak loudly and slowly enough so that I can understand. Thanks again. Bye.
All right. Can you hear us online? It's all good? Okay. We have a number of hands in the room. Dave is up here at the front, and the speakers will be looming behind him when they speak. So I think I saw Angie first. And yeah, Alyssa's going to come around with the microphone.
I wanted to ask my question since it's for Herve, and so you just finished and everybody's getting ready still. So this is really interesting what you've presented, and I just want you to assuage my concern, which I'm sure you've thought about. So your observational constraints, especially over land for the water cycle components, especially thinking about India, the Ganges. A lot of these things are probably very sensitive to the aerosol forcings that have already happened. And so have you thought about how to reconcile the uncertainty in what the past aerosol forcing has been with using your observational constraints going forward, also knowing that there's huge uncertainty in aerosols going forward?
Yes, thanks for the question. Yeah, it was highlighted by the IR6 that if you try to understand the historical evolution of the water cycle, the aerosol forcing is really important. And I fully agree with your comment. But what is nice with this KCC method is that, in fact, it can be easily applied in the same way. Sorry if I had not time to show that, but to the DAMIP experiments. So you can also use the method to better understand what is the role of the individual forcings, greenhouse gases versus aerosols, and if the model are too sensitive or not to some of those forcings using the observational constraint. So it's a way to be very consistent between the interpretation of the past and the interpretation of the future.
Okay, Rob? Yeah. Just come here.
Question for Dave. So in the introduction, you showed that the partitioning of the carbon uptake between the land and the ocean, but then when you're showing this huge uncertainty in the CO2 in the future projections, you were then only talking about land. So I was just wanting some kind of order of magnitude. How much can uncertainty in future CO2 come from the land sink versus the ocean sink, since there's not any ocean carbon cycle here as far as I know, and wondering if you have an answer for that.
Yeah.
Could possibly responses. Oh, it was a question for Dave? Yeah.
Yeah, but if you want to answer it.
Sorry, no. Well, maybe
Sonia.
Dave will say the same thing as me, but yeah, I would say personally, I think it's much more of the uncertainties in the land carbon cycle. It's kind of what I was showing in my presentation, that we have this huge uncertainty. I mean, yes, there is a lot of variability in the land carbon cycle, and additionally, we find that the models don't do a very good job at reproducing it.
Yep, that's what I was saying. Yeah, I'm not sure the exact number, but it's a factor of 5 or maybe larger, the uncertainty. And the ocean process is really, it's just this concentration-driven process mainly, which is why it's a simpler thing that ocean models can get right. But I tend to agree.
Okay, Hanjun?
So I have a question to Dr. Douville. So when you show the constraining effect of the runoff, it seems that in future projection, the runoff ratio is smaller after constraining, the projection. So do you know which model bias is responsible for that discrepancy in the runoff ratio?
So it's a question for me, I guess.
Yes.
Yeah.
Yes.
Okay. We did a previous study showing that if you want to constrain runoff under climate change, you should not rely on, for instance, on shorter timescales like interannual variability. And there was a nice study by, for instance, Flavio Lehner about this. But we have shown that the runoff elasticity to both temperature and precipitation is timescale dependent. Then what are the biases which are determinant, which drives the uncertainties? This is something that we didn't look carefully. We started by the high latitude rivers, where the signal to noise ratio is better, and where, of course, if you have, for instance, a bias in snow accumulation or things like that, you will have a different sensitivity to global warming. But I can't really answer. It's a very relevant question, and it's an issue with most of the constraining studies. They do not always explain the main mechanisms. Maybe what it means is that we sometimes need even more models rather than less models to find a robust explanation to that. And unfortunately, the explanation may be also model dependent, I would say.
Tiffany?
Thanks. Those are a great set of talks. I have a kind of a general philosophical question, though, maybe for all of us. The tension between some of these land surface discrepancies, in particular relative humidity, that have been known since CMIP 5, and the tension of trying to understand the current generation of models and why they exhibit discrepancies, versus moving on to a new generation of models that add more and more processes. So I'd love to hear your thoughts on, the land surface humidity discrepancy has been known since CMIP 5, and yet here it is again. So what's going to happen next if we just keep adding more processes and not nail it down?
So I could not understand everything, but what I understood is that it's not a new problem, and you are perfectly right. It was already emphasized about CMIP 5 models, and Sonia has kindly quoted one of my papers about this, and there was another paper by Dune et al. About this. This is the same story with the snow feedback. If you look at the first emergent constraint about the snow albedo feedback by Q et al., it has been applied to successive generation of model. It's physically well understood. It's robust. It's one of the most robust emergent constraints. And unfortunately, it does not translate in model improvement very quickly, which again emphasizes the need to have a stronger interaction between model users and model developers. I guess Dave Lawrence would agree with that. And in fact, it's a two-way interaction, because most of the issue we are trying to understand maybe have some simple answers that they could provide as well. So this is my this is true in my lab. These are not the same persons that are developing the model and that are looking at CMIP projections. And I guess it's true in many labs, and I think this is something we should think of.
Yeah, I have maybe also a point on this. Actually, my explanation is maybe when I see a lot of the studies who make some projections on how relative humidity is expected to change, I think sometimes it comes from a bit too much physics. I think some of what we are saying might be related to biology. So basically how plants react, both, both under enhanced CO2 passing, maybe even more importantly, when you have higher VPD in the air. So I think some of the problems might be related to basically representations, this impact of water limitation on the plants, and how these feedbacks basically are represented in the models.
Can I
Yeah.
add? Yeah, I agree with Sonia, and it's an interesting question, right? We struggle with this all the time, right, at NCAR, but adding processes versus, understanding things. And I think you could probably make the same
microphones on in the room.
biases that we're seeing in the trends for different things. On this particular one, one hypothesis we sort of had in this realm was that we aren't properly representing what Sonia mentioned, it's plant water stress, and because we aren't modeling the physical process, right? And so we added this thing called plant hydraulics. I think we're the only model in the CMET archive, and it didn't help. But there was some hypothesis it would, and now our theory is, well, we didn't parameterize it right, and so we're trying to re-parameterize it to bring it to something, project with Isla. It's still not looking like it's the solution to the problem, but it could have been. So that's a bit the way you have to think about these things, is there's sometimes the missing process could be the thing that is, in the case of the humidity problem that Isla has pointed out, I think really interesting about that problem is that all the models get it wrong, right? There's no model that's getting it right. So it really almost suggests there's a missing process. But we don't know exactly what that is yet.
Karen?
Yeah, thanks for the great talk. So a question for Dave. So one just clarifying question and then a more complete question. You talked about the observational constraint that really narrowed that PPE uncertainty. Can you just say what that was again and explain the observations? But I'll just do the second one also while I have the mic. The second question is, when you do that constraint, do you guys then go back to the parameters and look at kind of what parameters get kicked out? And can you interpret that part of it as well and say, okay, this kind of makes sense actually that maybe these were ones we didn't believe, or is it are the parameters already just kind of all reasonable ranges, so it's difficult to really kind of gut check that cut out of the parameter space?
Yeah, to be clear, when I tried to imply that it was a really quick and dirty analysis so far to see about the observational constraints, about whether they could give us anything, almost like we could have put any number in to see if we did know, historical carbon trend of the last 20 years, would it be a constraint? And so I used the paper, one of the papers I cited, which is showing the change in live woody biomass, which is, kind of a dominant control on the overall carbon stock trend of over a 20-year period, and applied that, without thinking about it hardly at all. So really just, but just to say, what could we possibly do? And then our idea is we will keep adding more and more constraints as we possibly can that might be useful, and we see that some are helping and some aren't. And of course, this was the carbon cycle, and the model is trying to do everything, right? So it may show up that it makes the carbon cycle look better, and the water cycle has gone to a complete disaster. So we still have to check things like that. In terms of the parameters, what we're really doing is actually much more complicated. We're trying to tune the model with a wide range of parameter sets, and there's a whole wave of tuning that will happen in our model, where you would kind of first do a first filtering, kind of get close, then resample, zero in on the region where the parameters look like they're kind of giving reasonable ranges, do it again, and we could end up we're estimating up to 10 waves of that cycle. And so each time you're hopefully going to learn something about your parameters, learn something about what a reasonable range is. But we still, everything so are pointing to the fact that we will not come down to one parameter set, or even something that looks like it could be very wide ranges of parameters, where one parameter goes high and the other parameter goes low, and that gives you a reasonable simulation. That's almost certainly going to happen. The other challenge there is that, for many of the parameters, we don't actually have good priors. So we're essentially guessing on the priors. We don't know what the reasonable range for this parameter is. So we do something like say, oh, let's assume it's plus or minus 20% or plus or minus 50%. Part of this is just getting closer to what the real truth of these parameters might be.
We'll take one last question from Jonah.
Excuse me, could you please?
Oh, sorry, I didn't see.
Microphones are on in the room. We cannot hear online.
Can you hear this microphone? No.
That's the microphone we're hearing. We're not hearing.
Yeah, we hear this one.
Okay, there in the front. Maybe repeat the question.
Okay,
so they hear.
Can you hear me in the virtual session? Okay, I have a question for Herve. You saw in one of the slides that fresher areas are getting fresher, but it seems that the saltier areas are not getting salter, that they maintain. So since salt must be conservative in the ocean, that must imply that the freshwater content is going from some Earth system component to another, and so maybe it's ice sheets, and it seems that it is happening since long time ago, because it's not something that is a change that it is now that the saltiers are keeping the value. So that's my question.
Oh, we're not hearing you. Are you muted?
Yes, thanks for the question. Yes, I'm not a specialist of the global ocean water cycle, but my understanding is that in my results, what is a challenge is the dry get drier over the ocean paradigm. That is, the salty get saltier, not the fresh get fresher. And in fact, the sea ice, not sorry, the ice sheet melting, sorry, is mostly contributing to have more fresh waters in the Northern Ocean, I guess, and so maybe has not such an obvious influence on the areas where evaporation exceeds precipitation. And in fact, if you use deciles of the salinity distribution, you see that in the very salty areas, you get saltier, but in at the margin of those salty areas, it's not so obvious that you will get saltier. And I guess it's as well related to the ocean dynamics, the vertical mixing within the ocean. Not sure it's related to high latitude and cryosphere mechanisms.
Yeah, there's a comment in the chat that it's just sea surface salinity, not the full 3D field, which I guess is what you're saying. So, okay, so we're out of time for this discussion. It's time for the coffee break. Thanks to speakers again for a great set of talks, and we'll come back at 10:30.
Right, so this session is thinking about kind of new methods, new approaches, new things we can try and do to tackle these problems. So we have a couple of talks to start with on kind of high resolution models and the Pacific problems that have been such a big focus here. And then we're going to hear a little bit about machine learning and a little bit about kind of seasonal hindcasts. So that's the plan. As normal, we'll have the questions at the end of the talks. And so first up, we have Ping Chang to tell us about high resolution modeling. Oh, okay. Right. I think we are just unmuted.
Well, thank you so much. And I just want to thank the organizer of the workshop. It's been a really nice experience for me, and I learned a lot during this past 3 days. And so I have the honor to kick off this final session. So I thought I'm going to do is to introduce you to a new set of ensembles. We use this high-resolution CSM model, generating a new ensemble of climate simulations. And this is work in progress. And I just going to give you some report, the progress we've made so far. And this is a big project, and we started it almost 4 years ago. It's a long way since we started, and a lot of people involved in this project. And it started off as international collaboration, and but a few years ago we transitioned that into a U.S.-only project. And for reasons I don't really want to talk about right here, we can talk about this offline if you're interested in this. So I just want to mention a few names here. I have a few collaborators listed here, and those people that contributed directly to the analysis I want to show today. And I just want to mention and acknowledge the support from NSF and the National Academy of Science, who's supporting this research right now. So to start off, I just want to give you a very brief introduction of the high-resolution CSM. And so the version we're using is 1.3. It's not the latest version 2.0. And for the reason that 1.3 computationally is cheaper, and it's already have a high resolution configured version we can use for this project. And as far as I know, there is no CESM2 high resolution version, and there's no plan to have high resolution version of the CESM2 at this point. So this is the version we're going to be using. And so the atmosphere resolution is 1/4 degrees, and the land resolution 1/4 degrees as well. And the big increased resolution is in the ocean. So for ocean, we're running global ocean model at 1/10 of a degree. And because we are running at such high resolution, one of the major changes we made in this simulation compared to the standard resolution CESM is the 80 parameterization. So we turned off all the 80 parameterization in this simulation. The only parameterization we kept in the ocean model is the KPP mixing in vertical. So I'm going to come back to that, and it turns out that seems to have a major impact. So just give you a quick rundown of the simulation we have done so far. And so the first simulation we did was the high resolution MIP simulation. Some of you may already know this, and so we contribute a set of tier 1, 2, and 3 simulation to the high resolution MIP. Those are relatively short simulations and has a control simulation using 1950 forcing, right? You all know. And the next set, which is much bigger, and this set is essentially the full deck, CMIP deck set. And the reason we did this is because we want to compare directly to the existing CESM large ensemble simulation. So the design and the protocol follows the standard design of the CESM large ensemble, very similar. So it includes a pre-industrial control simulation. We integrated a model high resolution for 650 years. And then we branched it out from this pre-industrial control simulation, and we made a 1850 to 2100 historical and future climate simulation under RCP 8.5. And then from that run, we generate a 9-member ensemble of runs. So this set is almost done, and we have a few more years left for the last ensemble. And but this set is basically done. And then we also made an ensemble of 6 right now, RCP 6.0 simulations. And our intent is to make ensemble of 10 6.0 simulations. So in addition to that, we have one single simulation of RCP 4.5 and one single simulation of RCP 2.6. And then we did 2 climate sensitivity runs, 1% CO2 per year, 150 years, and quadruple CO2 equilibrium climate sensitivity simulations, 150 years. And finally, we have ensemble of 3 AMIP simulation in a high resolution atmosphere only mode. So that's the list we have so far. And I hope that this set of simulation can be used to shed some light on the issues we're discussing in this workshop, right? So that's the hope. And the last set of simulation we did is a high resolution decadal prediction simulations. And so it consists of 2 parts. One is the 5 cycles of forced ocean sea ice FOSSI simulation starting from 1958 to 2018. I think Liz Marone introduced this set of simulation already in her talk. And we use this simulation to initialize our decadal prediction. Okay, and so the decadal prediction is ensemble of 5 years prediction and 10-member ensemble, and initialized from 1970 all the way to 2022, every other years. And we only initialize right now in November. So one initialization per year so far. And our intention is to extend this ensemble and make it more comprehensive. So if you're counting all those simulations together, we have 6,000 years accumulated simulation. We generated about 6 petabytes of data. So 1 year simulation, this model spit out about 1 terabyte of data, right? Lots of data to worry about. And so in case you're wondering what is the equivalent of the low resolution model simulation, so the cost ratio of the high resolution to low resolution is about 100. So one single simulation of high resolution is equivalent to ensemble of 100 low resolution simulation. So that's the cost. So those are very expensive runs and took a lot of time and effort to complete. All right, I hope you're not too tired of looking at this picture. We've been looking at this from the day one of this workshop, right? So that's the things I'm going to talk about today. So this is the trend problem, right? We see this, this is the observation, looking at the cooling trends in the South Pacific and the Eastern Tropical Pacific, and then the corresponding sea level pressure trends and the precipitation trends. And we all know that if you look at the low resolution model, we're not getting the similar trend response. So this is the similar analysis. By the way, all the analysis I'm going to show today is very simple, just the linear trend analysis. I don't do any fancy statistical analysis at this point yet. So should be very straightforward. So looking at the similar trend analysis for the low resolution model, and you can see that there's no evidence of the cooling trends at all. So this is CSM1 40 member large ensemble plus the 5 ensemble we ran for the comparison. The reason we have to run the low resolution for our simulations because the atmosphere dicore is different. And the standard CESM using the finite volume dicore, and high resolution, we're using the spectrum element dicore. So the dicore is different. So that's the reason why we actually rerun some of the low resolution so we can do an apple-to-apple comparison. And this is what happens if you increase the model resolution, right? So if you increase the model resolution, this is looking at ensemble of 10 historical simulations. Now you start to see that the model is getting the cooling trends, and it's getting the sea level pressure pattern, and it's getting the precipitation pattern, more like in observations, right? So Claire showed the other day in the beginning that there are lots of internal variability we expect, right? So I'm just going to show you each ensemble member of this. So I'm showing you 11 runs, and the one on the top is from the high resolution MIP runs. It has a 1950 control. And the rest of this is all the long simulation. The last one, the lower right corner is the ERS, that's the observation, right? So you can see lots of variability, but many of the ensemble are getting the cooling trends. And in particular, if you look this pair, so the last one we got, right, look almost like in observations, right? All right, so, but if you're counting if you look the individual runs, there are probably 8 members that tend to get the cooling trend, and 3, particularly number 7, did not get the cooling trend at all, right? So lots of variability. So not only we see the cooling trends in these long-term simulations, we also see similar improvements in our decadal prediction simulations. So this is a comparison of the ACC scores computed from the high-resolution decadal prediction set and the standard low-resolution DPLE prediction. And this is a figure from a paper Steve Younger published in last year. And so if you look the difference between the correlation scale of the two models, and most of the difference you can see the improvements is mainly in the Southern Ocean and in the equatorial Pacific Ocean, right? And so if you draw the box and take a look at what happened between the high res and the low res, here the blue is showing the model prediction. The black is showing the observed SST averaged in those two boxes in the Southern Ocean, right? So you can see that one of the major improvement of the high resolution model is that the high resolution model does not have this spurious warming trends the low resolution has, right? That's the reason why the model is getting better scale. And so here's the other box in the tropics. And one of the particular improvements we see is the equatorial SST gradient along the equator, which is a controlling factor for the Walker circulation. And the high resolution model is doing a much better job in capturing this gradient. In fact, if you look at the correlation is about 0.73 and for decadal prediction. So that's really good scale, right? So the high resolution model definitely is doing better job in doing that. And if you compute the trend from the high resolution prediction model and the low resolution prediction model, then you start to see this very obvious difference that in the low resolution model near the bottom, you see that the model is generating this warming trends in the Southern Ocean and in the equatorial Pacific. And high resolution model is doing much better. At least the trend is close to. It's not quite as negative as in the observation, but it's definitely a major improvement. So as the precipitation and the sea level pressure pattern. Right? So we're seeing the improvements not only in the long-term simulations, but also in the decadal prediction. So now the question is why, right? So since we changed the resolution in both atmosphere and in the ocean, so the question first you want to ask is the atmosphere or the ocean made a difference? So one thing we can do is by taking a look at the AMIP simulations. So we compare the two AMIP simulations we have, high res and the low res. The low res is in the middle. The high res is in the on the right. So we're looking at a trend analysis. Again, the trend at the top panel showing the zonal wind stress trend, and the middle showing the sea level pressure, and the bottom showing the precipitation trends, right? So if you look at the AMIP simulation, you get the impression that the high resolution model and the low resolution, they're very similar. In fact, you can even argue the low resolution model is getting even stronger trends in the high resolution model, even though you can argue that ensemble size may be too small, but 3 is better than nothing, right? So, so based on that, it seems to be that the atmosphere model is not really the cause of the improvement. What about the ocean, right? So we have another set of simulation where the FOSSI simulation, right? We force the ocean model using observed winds and the fluxes. And in this case, we force the ocean model, the high resolution model and low resolution model using the same atmosphere forcing from GRA 55, the OMIP simulation, right? So this is looking at the SST trends. The top panel is showing the high resolution model, the middle is showing the low resolution model. The bottom is showing the difference. Even though the difference is small, that's kind of expected, right? In the OMIP simulation, we're restoring the sea surface temperature to the surface air temperature. So these SSTs is not the best variable you want to really compare. But nevertheless, you see this difference even in the Southern Ocean. You see this tendency that high-resolution model tends to become driving a cooler trend, even in the AMIP model, right? The other more independent measure we can look is the sea ice. Sea ice is not constrained, right? So it's a model simulated response. So we're looking at a comparison of the Southern Ocean sea ice extent in JJAS season, and the solid line is showing the observed sea ice, and the dotted line is showing the model simulated. Just you can ignore all the color line. The colored line showing the prediction. We don't have to worry about for this purpose. So you can see the high resolution model seem to be able to capturing the upward trends of the sea ice quite nicely, right? And what about low resolution model? Here's the comparison between the lower same forcing, right? The low resolution model showing a much weaker trends, right? The red is the low resolution model. The black is the high resolution model. You can see there's almost factor 3 or 4 difference in the linear trends. So the question is that why the low resolution ocean model tends to simulating a warming ocean in the Southern Ocean. And one of the reasons we think is the meridional ocean heat transport. So we computed the ocean heat transport, and this is a comparison of the meridional ocean heat transport in the Southern Ocean. And the left is showing the low resolution model, and the right is showing the high resolution model. The top panel is showing the total heat transport and averaged in the period of 1979 to 2017. So if you look this chart, right, you see very clearly that the low resolution model simulating almost twice as much poleward heat transport, right? So there's significantly more ocean heat transport towards the Southern Ocean in a low resolution compared to the high resolution model, right? So if we decompose the ocean heat transport into a mean circulation induced heat transport versus the eddy induced heat transport, then you see a really large difference. This is indicated by the blue line here. You can see that low resolution model, the eddy heat transport is significantly larger than the meridional heat transport in the high resolution model. So there's a very clear difference in the parameterized ocean heat transport in a low resolution model, right? And even more, the bottom panel here showing the trends, and there's a very large difference in the heat transport trends between the high resolution model and the low resolution model. And the high resolution model showing a large positive trend, meaning that there's a consistently decrease of the southward heat transport during the recent decades. And most of those, the trend is coming from the mean ocean heat transport, not coming from the ocean eddy induced heat transport. Where in the low resolution model, first of all, we see a much less trend. And the second thing we see is that there is a compensation between the mean flow and eddy induced heat transport. They almost tend to cancel to each other, right? So that's another major difference here. All right, so now what we can take a look is our high resolution model seem to getting a better simulation of the recent decade trends, right? What about in the future, since we integrated the model all the way to the end of the century? One of the questions we want to know is that whether this cooling trend is going to persist, right? Are we going to get a cooling trend, a warming trend towards the end of the century? The answer is that if you look the end of the century, both the high-resolution model and the low-resolution model generating warming trends. There's actually very little difference, right? So the cooling trends we see in the recent decades seem to be a transient phenomenon, at least according to this set of model simulation. So that leads us to the question, why? Well, one of the things we explored, I was a little bit surprised to see in this workshop, nobody talk about the ozone yet. So this is the thing I'm going to talk about. And so we did one of the obvious reasons for us was think maybe it was because of the ozone forcing, right? There was a ozone hole developed in the early 70s. We see onsets of the ozone hole, and obviously this ozone.
Talk about the ozone hole briefly, please.
I'm assuming everybody knows that. I want to have 20 minutes, right? So,
Yeah, we're a little over.
oh, it's already?
Yeah,
oh, I'm sorry.
That's right.
Oh, all right. So,
it's fascinating stuff, but wrap up in a minute or two. That's
okay. So, well, then I really, so then I'm just going to tell you the story, and the story is that if we did a experiment where we hold ozone constant after the 1970s. So what happened is that if you're holding the ozone constant, then the cooling trends start to disappear. You can see this is again the right panel, the left panel is showing the control simulation versus the ozone constant ozone simulations. You can see as soon as you're putting the ozone constant, there's no cooling trends anymore, both in the Southern Ocean and in the equatorial region. And we're getting a much less strengthening of the zonal winds. You can see the sea level pressure gradients getting a lot weaker, right? So, and then the question is that, is there a inference of the Southern Ocean to the equatorial region? And one of the things one can look is taking a look at the Hofmüller diagram and averaged over this zonal box here. And you can see there seems to be somewhat a propagation with the Southern Ocean leading the tropics by about 5 years. So that's, we think that the ozone maybe is really driving this cooling trends. Right, so wrapping up. So this is just a story. I'm going to stop here.
That's fine. Put up the summary. That's fine.
All right, so let me show the 3 points you wanted me to talk about. The good is that the model is improved in getting the cooling trend correctly when we increase the horizontal resolution. The bad is that when we increase the high resolution, when we increase model resolution, the Southern Ocean warm bias did not improve. In fact, it's getting even worse, right? And the really ugly thing is the ocean heat transport. There's a very large inconsistent between the high resolution model and the low resolution model. So that raises the question that, are we doing the right thing for the eddy parameterization in the low resolution model? Right? The even worse news is that, as far as I know, there's no direct measurements of the eddy heat transport in the ocean. So how are we going to confront this issue is going to be a big challenge. Anyway, I'll stop here. Thank you.
So one of the great things of being here in Boulder is that you can bump into people in parking lots or coffee shops and talk about climate and models. Last year I bumped into Gokhan in the NCAR parking lot, and I always had this hunch about how you could cool the tropical Pacific in response to external forcings, but there was no evidence in the climate models. So I asked them if I could take a look at the high-res simulations that Ping just showed. I'm gonna make this taller. Okay, I'm gonna get further away. So I think there's so many proposed mechanisms, right, to understand how the Pacific can cool despite the rest of the world warming. And But those mechanisms in the literature don't arise spontaneously in couple models, so it's hard to establish causation, and Ping just showed evidence it could be ozone. So we need a model, and this is what just Ping showed, and I'm showing the 4-member average because this is what I worked with until a few weeks ago. And it was hard to tell with 4 members, the first 4 members, what was going on. But you can see that it looks very much like what Ping showed with the first 4 members. The 1 high-res MIP and the first 3 runs. Back then I did some bootstrapping to convince myself this was forced. Now I think everyone is pretty convinced after seeing Ping's results that almost all members look the same. The circles show you, and the reason why I'm showing this is because I'm going to show another ensemble, which is also small. And this bootstrapping of the low resolution large ensemble, which is almost the same model, but with lower horizontal resolution. With the 40 members, so where there's an open circle, there's no way you can create a 4-member ensemble with a 40-member large ensemble. It's just, that will look like this 4-member ensemble. So I'm going to start with the mechanism, and then I'll show some evidence. And I took a different approach that Ping followed. Instead of looking at ocean and atmosphere coupled, I just looked at an ensemble that has mixed resolution. The atmosphere is higher, the ocean is lower. But this is the same runs, essentially the same pattern that Ping showed. And over the last few days, I tried to put together everything that was discussed in the workshop to see if we can make sense of what these simulations do relative to what all of you have shown. So I'm going to show, what I want to show is why is this response so strong in the high-res model relative to the low-res models. And what I'm proposing is there's 2-way feedback between the tropics and the extratropics. This is not my idea. It's in Yu Dong's paper a few years ago, how the equator, the tropics, the subtropics, the high latitude, South Pacific, all interact with each other via atmospheric and oceanic pathways to create these bigger responses. But you can think it starts in the subtropics. This was, perhaps it can start in the Southern Ocean too. But it's a feedback, so you can excite it anywhere along this loop. Ways to excite it is by this differential in thermodynamic damping that goes back to a paper by Julie Leloup and Amy Clement. All the subtropical regions have higher wind speeds, so if you impose a uniform warming, they're going to warm less. Not cool, but at least warm less, and that can trigger responses in the atmosphere. Allen had a poster on Monday showing that when you just consider this mechanism, you get a pattern that looks like observations, but it's not as strong, so something has to amplify it. Yen Ting had a poster and a presentation on a CGD seminar on Tuesday that you could excite this pattern also by the response in the zonal mean Hadley cell. If the northern hemisphere warms, you're going to strengthen the zonal mean Hadley cell, and it will strengthen the northerly component of the southeast trades. Can also produce cooling. And you see that in these simulations that cooling stretches all the way to the equator. That's evidence of a west feedback active. I'm going to show you more evidence later with the winds. Once you get there, you're creating temperature gradients. And the most important one, you saw it in Ping's diagrams, it produces that shift in the SPCC, the South Pacific Convergence Zone, a shift towards the pole, to the southern pole, because you're cooling the equator relative to the off the equator, so the rainfall will move away from the equator. It's in the observations and in these simulations, and that can trigger stationary wave, a teleconnection to the southern hemisphere. We see it every La Nina event, so this is not surprising, creating, especially in the Southern Ocean, that high and low pressure response. I'm showing it in schematic form here, but the model does it. You saw it also in Ping's plots. I'm going to show them later. That would strengthen the westerlies locally, in addition to the effect of ozone depletion, for instance, on the SAM, but at least there's this local intensification of the westerlies, which we also see in observations, and it's quite intriguing. It has been attributed to the tropical SSTs by work by Clara and Dave Schneider, perhaps others. It's really hard to keep everyone that has worked on this problem in one presentation. So don't get mad at me if I don't cite you. I try to put it. And then you can produce cooling, like Ping showed, because of all these responses in eddy, meridional eddy heat transports, and this idea, and then once you produce cooling, that cooling can be advected in the subtropics, like in Yu's paper. That was the idea, that this two-way feedback would be excited here in the Southern Ocean. And then that cooling makes it to the subtropics, and you're back to the beginning in a positive way, so this can make this response stronger. So that's kind of what I want to present today, and I'll show you evidence for this. Also, you have the westerlies, and they're going to interact with the Andes and produce high pressure, an anomalous high in the South Pacific. We saw it also in the response in the SLP plots that you just saw, and that would also strengthen the Southeast trades, reinforcing the cooling. So this is my proposal for a two-way feedback, that the low-res models, now we call them low-res, the standard res, the CMIP models, do not simulate for some reason, creating this weaker force response. I think this response could also be Alexis thermostat, just like a transient response to the greenhouse gas forcing, and because of this two-way feedback in the models, it gets stronger, and perhaps we can see it here, and you don't have to look at the transient part like Alexis did in their analysis. And then that will produce cooling. So I'm going to skip this, and I'll show you. So essentially, I compared 3 ensembles: the classic large ensemble with the 40 members, standard res, the high resolution ensemble that Ping just showed, and there's a mixed resolution ensemble, because to tease out the effect of oceanic and atmospheric resolution. So this is another benefit of just hanging out at NCAR often, is you can bump into people that run things. And this ensemble, the mixed resolution ensemble, I call it HRLR. It's the same resolution in the atmosphere, but back to the 1 degree ocean, in the ocean. And the simulations are exact same forcing. And the only issue is that there's only 3 members of that mixed resolution large ensemble. So take some of my results with a massive grain of salt, because it's only 3 members. We're running more. They're super expensive, because most of the computational cost in these simulations comes from the atmosphere. So we're running, hopefully, at least 1 more, 2 more, to be sure that what the mixed resolution ensemble is showing makes sense. And the analysis interval is the period with the trends that we have just been obsessing with lately. So similar to what Ping showed, those are the 3 configurations of CSM with different resolution. And with again, I'm using 4 high-res, full high-res, because that's when I did the analysis. There's more now. And in the middle, you have the mixed resolution ensemble, which there's less members. The stippling here, the open circles is when it's totally outside the distribution of the 40-member standard resolution large ensemble, and the little dots is when it's outside, when you still have a 5% chance of getting this response with the sampling 3 members from the 40-member large ensemble. So you can see we're not so confident that those responses are distinct than what the standard resolution large ensemble does, but there's a hint that there's something going on, and the pattern looks very similar. So this is in some disagreement with what Ping shows. So we're still trying to figure out what's going on with this mixed resolution ensemble. But you see that the essence of the response is there, just with increasing the resolution in the atmosphere. And same thing with SLP, Ping showed similar plots, but in the middle you have this mixed resolution ensemble. And rainfall. So there's something in the atmosphere also, an improvement in the simulation of the climate that comes from increasing atmospheric resolution that leads to some of these improvements. So just to show you more evidence about the mechanism, I changed the order. So now on the left, I'm starting with the standard res, going to the right to the high res and then the observations. I get closer and I'm focusing on the austral winter and spring response. So this would be, I'm from the southern hemisphere, so austral winter, it's June, July, August, September, October, November. I split it in 2 seasons because the next half of the year is the erroneous year, part of the year. This part of the year, things work great. And there's an addition in this plot. I'm showing winds, and again, these are changes, and I'm showing in contours, the solid contours are the rainfall contours, same rainfall contours for the climatology. So that tells you where the climatological SPCC and ITCC are. So you can see that a lot of the responses, the structure is similar. I'm surprised we ignore this when we looked at the low res or the CMIP models, that during these seasons, there's a response that is similar to observe, a lot weaker, but the winds and the pattern of cooling is quite similar, with the exception of the strong cooling perhaps in the South Pacific, in the full high resolution ensemble. But even the winds, the strengthening, the local strengthening of the westerlies in the South Pacific, and the evidence of a west feedback, right? Strengthening of the southeast trades, following the SST gradients, propagating into the western equatorial Pacific. So here, in all plots. And that's because that is a suggestion of the west feedback propagating following the climatological traits. And then the opposite season, when the CMIP models, including CSM1 at the standard resolution, have the double ITCC. So I want you to focus on this plot to the left, where in the contours, you can clearly see the double ITCC in the erroneously in the South Pacific, in the southeastern Pacific. Still, the high-res model doesn't get an extremely realistic SPCC, but it's a lot better. And that tells you that in the 2 configurations that have a high-resolution atmosphere, there's no double ITCC blocking the propagation of signals from the southeast Pacific. So your west feedback can propagate the SST anomalies and the wind anomalies all the way to the equator, which you can see in the simulations. Again, keep taking my mixed resolution ensemble with a grain of salt. It's a 3-member ensemble. Perhaps we just got lucky. When we finally publish this, we're going to have more members, and hopefully these results hold. So again, there's this 2-way feedback that gets stronger in the high-res model because of a better representation of the ITCC mainly, and produces a much stronger externally forced response that infers from the standard resolution models. The forcing is still unclear for ping is ozone, could be also a role for aerosols and greenhouse gases in a way of the thermostat idea. And therefore the conclusion is that improving all these ocean-atmosphere topography interactions might be key to simulate force modes, and particularly the double ITCC. I think we've been very naive about the double ITCC error in CMIP models not being a problem for the response. But I think this shows that it's a big issue. And the same mode, so this mode that it's driven by this 2-way feedback, could be excited by noise. And indeed, in the high-res model, if you look at the control, Pacific decadal variability is a lot stronger. So there's also an impact on the internal variability. And I think with that, I'll stop. And yeah, excited to hear what you think.
So thank you for the introduction. So in this talk, I would like to approach the issue of the good, the bad, and the ugly from a different angle. And I'll use the statistical learning approach to relate the tropospheric stability and the surface temperature warming pattern. And this work is collaborated with Mark Zelinkat and Steve Pochadley. So started from the cloud feedback. We know that cloud feedback have large spread in the global climate models. And one of the reasons is because it depends on not just the global mean surface temperature, but also on the tropospheric stability, or EIS, which itself is governed by the evolving surface temperature warming pattern, and that is known as the pattern effect. So one of the popular approach to reduce the uncertainty in cloud feedback is using the historical record. However, because the surface warming pattern in historical period and future warming scenario are different, it is important to first quantify the strength of pattern effect, such that we can further do the emergent constraint. And to do so, we need to first better understanding what drives the strength of pattern effect, and it mostly depends on how the EIS will respond to the warming. So with that, how does the pattern relate to EIS and then related to the cloud feedback? Here's a simple diagram to explain that. So here we have the Western Pacific, which is characterized with deep convection cloud, and then the Eastern Pacific have a lot of low-level cloud typically. And there's the temperature vertical profile could look like generally. And if there is more warming concentrated in the Western Pacific, this energy could be transferred to the upper atmosphere, free troposphere. It could warm up the free troposphere and also transfer to the remote region. So like the Eastern Pacific, free troposphere also be affected. But the energy cannot be efficiently affect the lower region in the Eastern Pacific, like the surface area. So this leads to is a increase in inversion strength in Eastern Pacific. What it will do is it will favor more development of low-level cloud and more solar radiation reflected back to the space and leading to a more positive cloud feedback. Well, on the other hand, if we have more warming concentrated in the Eastern Pacific, the warming could warm up the near surface layers of atmosphere, but could not be transferred efficiently to the upper free troposphere and remote region. What it leads to is a decrease in inversion strength, and therefore a less cloudiness and a more positive cloud feedback. So with that knowledge, if we focus on the low cloud feedback and then we define the pattern effect of low cloud feedback as the low cloud feedback simulated in 4 times CO2 simulations minus the low cloud feedback in the historical period. So that's how we determine the pattern effect. And then we regress that against the EIS-DT, the response of EIS to global mean surface temperature warming in the historical period, 1980 to 2014. What would we expect to see? Well, if there is a small increase in EIS with warming in the historical period, this will lead to a more positive historical cloud feedback. And because the cloud feedback in 4 times CO2 simulation is not changed, we just minus a more positive values. So this could lead to a small pattern effect. Well, on the other hand, if we have a large increase in EIS with warming in historical period, this could lead to a more negative or less positive historical cloud feedback, such that it will lead to a larger pattern effect. So we will expect these two quantities to have a positive correlation. So Tim Myers et al. 2023 have focused on the low cloud feedback pattern effect, and they're trying to use the observation to constrain that. So that including using the observational cloud controlling factor to calculate the cloud feedback, and also rely on the real analysis data set when calculating the historical part. So I'm plotting this figure based on the values in their studies. And indeed, there is a positive correlation between the pattern effect, the strength of pattern effect, and the change of EIS with warming. But they also show the result is that there is a widespread in the estimation of the EIS-DT in different real analysis data sets. This could range from minus 0.02 to 0.74 K per K, and that's widespread, limiting the ability to constrain the strength of pattern effect using the real analysis. So this also highlights that our understanding of how EIS respond to warming is still limited. So with that, and also given that Steve Pacelli et al.'s work, which he have gave a talk in Wednesday morning, he have showed that the machine learning could be a useful tool to predict the mid-troposphere temperature using the surface temperature warming patterns. So following that, the main purpose of this study is to use the statistical learning approach to relate the surface warming pattern to EIS changes and to gain some insight into the reliability of the reanalysis derived EIS. So started with how could we do that? To build up the machine learning, we need to have some larger data sets. So we chose 9 symmetric couple model simulations that have at least 10 ensemble members for each models. And then we trained the period from 1979 to 2022 using the historical and SSB 370 simulations. I didn't write it here, but the testing period is 1980 to 2014, which is the same period as all of the reanalysis are available. And in this case, the predictor will be the annual anomaly of global surface temperature pattern. And the predictant is the annual anomaly of tropical averaged ocean EIS values. So we are using a map to predict a value at each time step. And to avoid overfitting, whenever we are testing one models, we use the leave one out approach. So it's like if we focus on, if we want to test one models, we use the rest of 8 models to be the training data sets. So in this case, the input to the machine learning will be the annual anomaly global surface temperature pattern, and the number of that will be 9 models multiplied by 10 ensemble members for each models, and then multiplied by the number of years that we input. And the predictor, the output, will be the values of EIS values. And we use the method of partial least squared regression, or PLS. We also test a more complex methodology like neural network, and we found the result to be consistent. So once we have trained this machine learning framework, we can focus back on the model that we are interested in, and the input will be the patterns of all ensemble members and of the number of years, and let it to predict the EIS time series for all of the ensemble members for that models. And if we loop this process for all of the models, eventually we will get 9 trained machine learning framework. From there, we can plug into the surface temperature pattern from the observation from different reanalysis data sets and let it to predict the EIS time series. Eventually, what we care about is the metric of how the EIS sensitivity to the global mean surface temperature warming, the DEISDT. So we perform the regression of predicted EIS time series against the actual global mean surface temperature anomaly time series to get the DEISDT. So here is the first part of the results. So again, step by step, if we want to focus on one models, here is MyRock ES2L as an example. So we use the rest of 8 models as a training data set to train the machine learning framework. And then we use the MyRock ES2L warming pattern as an input. That is to predict the EIS time series. And then we calculate the predicted DEISDT as the predicted EIS time series against the global mean surface temperature time series in MyRock ES2L to get the predicted DEISDT, which is the x-axis. Similar method for the actual DEISDT is just using the actual EIS time series in the MyRock ES2L models. And we do that for all of the ensemble. So like each marker is one ensemble member, and loop this same method to all of the models. Here is the result. So the overall correlation coefficient is 0.92 between predicted and actual DEISDT. Once we have built up this trend framework, we can move on to the reanalysis part. So again, we have 9 trained machine learning framework. So for individual reanalysis data sets, the input will be the global surface temperature pattern from the reanalysis data sets, and then input individually into 9 machine learning frameworks. And then it will predict it. The output, eventual product will be 9 values of predicted DEISDT. And then we plot the range of that result. So here is the range of predicted DEISDT for 7 reanalysis data sets. And then the blue shading bar is like the range of that different uncertainty for the observations. So the final, like the ultimate goal is that we want to have some estimate of the DEI-SDT based on real analysis information and what we learned from the machine learning. So we use a method that is similar that we use in emergent constraint by Cox-Exel 2018. So we combine the observational uncertainty, which is the blue shading bar here, combine that with the prediction error based on the models and the machine learning, like what we learned from the machine learning, to get a likelihood of reanalysis-based DEI-SDT values. And we provide the central estimated and the uncertainty range of that likelihood. And we can plot the actual raw DEI-SDT values based on the raw reanalysis data sets. You can see, like, for example, the MARA2 have a weekly negative DEI-SDT in the historical period, and that is right really outside the likelihood range. And also, like, MARA and GRI55 have a positive DEI-SDT values, and that is also like outside the likelihood range. While the CFSR, the MRE3, and the ERR interim are fall within the likelihood range. So what could these results help us to resolve the problem? So back to the motivation of the study is that we found there's a large spread in DEI-SDT in realness data sets, which limited the ability to constrain the pattern effect, the local feedback pattern effect. And that pattern effect could range from 0.01 to 1.57 watts per meter squared per K. If we use the information that we learned from this approach, we can reduce that spread to 0.55, which is based on the error interim, to 0.95 based on the CFSR values. So that is a huge reduction in the strength of pattern effect. So quick summary of the studies. This is based on Tim Myers found that the observationally constrained estimate of local feedback pattern effect over the historical period have this wide range, and that is mainly because the real analysis strongly disagree with the recent EIS trend. And in this study, we trained the statistical learning algorithm to a field of diverse GCM to learn how EIS anomalies relate to temperature pattern. And then we apply that to the observed surface temperature pattern to estimate the observationally constrained DEI-SDT values. And our approach then predict the DEI-SDT values over 1980 to 2014 to from 0.25 to 0.53. And that is roughly a 1/3 reduction from the row spread of across the reanalysis data set. And from that, that's also implied a much tighter observationally constrained local feedback pattern effect of 0.55 to 0.95 watts per meter squared per K. And also that's value is based on Myers et al. So Myers et al. Also like give an estimation of the total pattern effect. And from there, the total pattern effect will be about 1.622 watts per meter squared based on these studies. And finally, we still want to notice some caveat in this study. That is the credibility of this result will be dependent on several assumptions. Some assumption could be big. So this including that the GCMs need to be realistically simulating the relationship between the EIS and the surface temperature patterns. And also the estimation rely on the accuracy of the machine learning approach that we use to learn the relationship. And the uncertainty could also come from the reliability of surface temperature patterns in the observational data set reanalysis. But still, we hope that this approach could provide some insights or some ideas into how we can use of the data sets, of the tools we have to confronting the problems and reduce the uncertainty. So with that, happy to take any question in the discussion sections.
Yeah, thank you. Yeah, glad to be able to give the last talk of this workshop. This is going to be work that I've been doing at NOAA Physical Sciences Laboratory here in Boulder with Matt Newman and Andy Hoyle. So I didn't think I could let this workshop end without showing this image one more time. I know that everyone would want to see it just once more. And as we've heard during the last few days, there's been a number of different reasons proposed for this discrepancy in the trends in the tropical Pacific. This includes sampling issues and errors in model internal variability, both in terms of the length of the observational record and also the model's ability to reproduce that internal variability. It's also been suggested that these errors are transient and that over time that the observed trend will begin to look more like the models. And also, other people suggested that errors may be teleconnected from other regions. And again, I think we've heard some of this today, such as errors in the Southern Ocean being teleconnected to the tropical Pacific. And it also could be due to errors in things like forcing fields, such as CO2 and aerosols. Or it could just be that the models are just getting this wrong. But all of these things are quite hard to test in free-running simulations. So one of the things we've been trying to do is to look at how these errors compare in seasonal forecasts. So we know that seasonal forecasts are also known to have mean biases that develop rapidly and quite quickly saturate. So I've got a couple of images on this slide. So the image in the bottom left here shows the global mean sea surface temperature in the CEAS-5 model, and just focus on the black line. The black line is the observations, which is what you can see at the top here. And if you just focus on the red lines, which are for the full initialization of the CEAS-5 model, you can see that even within the first month, the model quickly diverges from the observations and very rapidly enters its own model state. This image on the right here is from a more recent paper, and it shows mean biases in a number of different North American multi-model ensemble seasonal forecasts. And you can see that mean biases develop within the first month of these forecasts and quite quickly saturate, and by around month 4 or 5, they've more or less saturated. And it has also been shown that these models also exhibit trend errors. And this is another figure from that paper, and it now shows the trend error in the tropical Pacific. And you can see that all of these models develop an El Nino-like trend error in the tropical Pacific. But the focus of this particular paper was more on the impact of these trend errors on skid in the tropical Pacific rather than linking them to climate model errors. And so today I'm going to show that seasonal forecasts have systematic global trend errors, and that these trend errors are very similar to the trend errors that we see in climate models. I'm going to show that these errors develop very rapidly, and I'm going to suggest that these trend errors reflect the sensitivity of the model mean biases to the changing initial condition radiative forcings present in each hindcast run, such as CO2 and aerosols. So that as the radiative forcing in each initialization changes, the mean model biases change, which leads to an apparent trend error. So I'm going to be using data from 11 different seasonal forecast models, which are listed here. We use the common period of 1993 to 2016. And some of these models are part of the Copernicus system. Some are North American multi-model ensemble models, and some are actually part of both model sets. I'm going to be looking at 4 different initializations, March, June, September, and December. And I'm going to be comparing these seasonal forecast models to 38 CMIP6 models. And I'm going to cover the same period as the common period. I'm going to be using historical years from 1993 to 2014 and the SSP 245 for 2015 to 2016. And while none of these seasonal forecast models that we use are identical to any of the individual CMIP6 models, they all use the same radiative forcings from the CMIP5 or CMIP6 models. So now I'm just going to explain briefly what we mean by trend error in this context. So we define a trend error as the slope of the linear line of best fit of the model error time series, so model error being model minus observations. And this is the same as taking the difference between the slopes of the model and observed regressions. So to illustrate this, I've got an example here for Western US precipitation in DJF. This panel on the left here shows observations in the black and the multi-model mean in the red. And you can see that the observations have a fairly strong negative trend, whereas that's not captured by the multi-model mean at all. And this would be a positive trend error. And this is actually, and on the right here, I'm now plotting the model error in precip in DJF for the multi-model mean. And the slope of this line is the same as taking the difference of the slopes of these two lines. So the trend of the error is the same as the error of the trend. And I'm going to be largely focusing on seasonal mean trend errors averaged over leads of 4 to 6 months. And significance is computed using this particular modification to the Mann-Kendall trend test. So first up, I'm just going to show the multi-model mean trend errors in the seasonal forecasts, which is shown on the right here. So the top left panel shows the September initialization, DJF verification. The top right shows December initialization, March, April, May verification, and so on. And what you see is that in all seasons, models have significant SST trend errors. In DJF JJA and SON, these look like the El Nino-like trend error that we see in climate models. And it's also worth pointing out that the pattern of trend error across different individual seasonal forecast models is very consistent. So based on this pattern, we identify we create a number of indices, which are shown as boxes on here, and I'm going to show a few examples of those on the next slide. So I've got a few regions shown on here. So top left is Equatorial Pacific, top right is Atlantic Nino, bottom left is Gulf Stream, and bottom right is Southern Ocean. And on each of these panels, there are 4 columns showing 4 different verification seasons, which are listed at the top of each column. And within each of these columns, the different colored symbols show the trend error in individual seasonal forecast models. The box plots show the CMIP6 model distribution of the trend errors, and the black points are for 2 other observational based data sets relative to ERA 5, which we use for the baseline here, just to give an indication of observational uncertainty. And what we see is that for all of these different regions, the CMIP6 ensemble closely lines up with the seasonal forecast models. It's also noticeable that in the seasonal forecast models, there's quite strong agreement in sign, if not always magnitude, across different regions and seasons. And these trend errors, you also see similar trend errors in sea level pressure, so that's what I'm showing here now, so sea level pressure maps. And you see that, for example, in DJF, we see negative trend error in the North Pacific, which is links to an anomalous deepening of the Aleutian low. And there are also patterns that project onto the Arctic Oscillation and the North Atlantic Oscillation in various different seasons. And again, I've got a couple of example indices for sea level pressure here. So I've got the Arctic Oscillation and the North Pacific Index, which is a measure of the strength of the Aleutian low. And you can see that once again, the seasonal forecast models and the CMIP6 models line up pretty closely, including changes in sign. For example, for the Arctic Oscillation Index here, you can see it goes from a negative trend error in March, April, May to a positive trend error in JJA. And there are also associated significant precipitation trend errors, which is now what I'm showing on this slide. And these errors largely line up and agree with the SST and sea level pressure errors that we saw before. In some regions, these look like the canonical El Nino signal, for example, here in the western US in DJF, or they align with the climatological wet season, such as in the case of Western Equatorial Africa in JJA. And once again, the pattern of the trend error across the different seasonal forecast models is really, really consistent. And again, I've got a few example indices which were defined based on the trend error patterns that we see here. And actually, when we look at precipitation, the hindcast and the CMIP6 models actually agree even stronger than they do for SST. And also, the median values for the CMIP6 ensemble often line up with the ensemble mean values for the seasonal forecast models, which are shown by the black diamond. And once again, you see that there's very consistent changes in sign across the 2 different sets of models as well. For example, for Southeast Asia, the trend error goes from negative in March, April, May to positive, and then back to negative, and this is closely mirrored in the CMIP6 ensemble. So I'm now going to show what these trend errors look like on a monthly timescale. I'm going to show that they're actually quite well developed, often at short leads. So this plot here now is showing the monthly trend error for the multi-model mean, just for the North Indian Ocean index that we defined for SST. On the x-axis now is the verification month from January through to December, and the y-axis is the trend error. The different colored lines show different initializations for the seasonal forecast model. So the blue line is March initialization, the orange line is June initialization, the green line is September initialization, and the red line is for December initialization. And I'm just going to put up the other regions, a few other regions as well now. So I've got 3 SST regions at the top here, 2 precipitation regions, and a sea level pressure region. And you see that the pattern of the magnitude of the trend errors actually follow quite a similar seasonal cycle across the different initializations. For example, if you look at Western US verifying in June, you can see that the magnitude of the trend error in the first month of the June initialization is very similar to the magnitude of the trend error in the 4th month of the March initialization. So this is indicating that there's a really strong seasonal dependence of these trend errors on the seasonal cycle. And it's also, you can also see that this dependence of on the seasonal cycle is perhaps a little bit more clear for precipitation and sea level pressure than it is for SST. And this suggests that maybe the SST errors are still ramping up a little bit. And this may suggest that these errors are developing faster in the atmosphere than the ocean, maybe developing in the atmosphere first. So I'm now going to link these trend errors to changes in the model mean bias that I mentioned at the start of the talk. So now what I'm showing here are a time series of different indices for 4 different SST regions in the top row and 4 different precipitation regions in the bottom row for different verification seasons. And again, these are leads of 4 to 6 months. And black line, as in the earlier slide, the black line is the observations and the red line is the multi-model mean. And you can see that in some regions where you have a positive trend error, such as the North Indian Ocean, you can see that this actually also is like aligns with a reduction of the mean bias from early in the hindcast period to late in the hindcast period. In other regions where you also have a positive trend error, such as the Atlantic Nino region here, you can see that this actually manifests as an increase in the mean bias between the first half of the hindcast period and the second half of the hindcast period. And whereas in others, the mean bias actually changes sign between 1993 and 2016, such as in the case of Western US here. And this link between the mean bias, changes to the mean bias and the trend errors is more easily seen for the longer hindcast period that we have for ECMWF CEAS5. So now at the top right, I'm simply showing the trend error as calculated before for the earlier maps, but instead I'm doing it over the full hindcast period of 1981 to 2016. And you can see that this model, so this is September initialization verifying in DJF, and you see that this model also has an El Nino-like trend error in this season. But then instead we simply take the difference in the mean bias between the early part of the hindcast period, so 1991 to 1998, so the first 18 years, the mean bias in the second half of the hindcast period, so the second 18 years. We take the mean bias in those two periods and take the difference between the two. This map at the bottom right is what we get. And you can see that the magnitude and the pattern of these two maps are very, very similar. And this suggests that these trend errors are representing a roughly linear change in the mean bias due to the time evolving radiative conditions in each hindcast run, which, as I mentioned earlier, these radiative conditions are the same as in CMIP6 simulations. So that brings me to my summary. So we've seen that seasonal forecasts have trend errors that are very similar to climate model trend errors. Shown these errors are very closely tied to the seasonal cycle, and this is consistent with models transitioning from nature's attractor to the climate model attractor. As these forecasts are initialized from observations every month, this similarity suggests that the errors that we see in climate models aren't due to unrepresented internal variability or that they're transient, but they are in fact model errors. And we suggest that these trend errors reflect the sensitivity of model mean biases to changing radiative forcings. As I said before, both the initialized and uninitialized models contain the same historical external forcings. And then finally, just a few implications of what we think the implications of this work are. So we think that those who are looking at climate model trend errors would really benefit from looking at the early development of these trend errors in seasonal forecasts. We've seen that there's a really close similarity between the CMIP6 models and the seasonal forecast models, and you can imagine how it would be a lot easier to analyze where the model might be going wrong by looking at seasonal hindcasts when looking at these trend errors. The hindcast period we've used here is relatively short. We don't think it actually makes much of a difference. We did look at using all the years for each model, and it didn't seem to make too much difference to our results, but we do think that it would be very beneficial if future hindcasts were run out for longer, maybe 30 or 40 years instead of the 23, 24 years that we have currently. And we also think that any climate models that are used for projection should also be run as seasonal forecast models. And this has a number of benefits. For a start, you don't need to run your model for as long. We heard earlier today about how much data it takes, how long it takes to run these models, how expensive it is to run these models, climate models for long simulations. And so, yeah, this reduces the computing costs and also speeds up the production of the data. It also means you can have larger ensembles as well. And it also means that any evaluation of changes to things like model physics or parameterizations will be more efficient because you'd be able to make a change, run the model, and then more quickly analyze the output, see what the impacts of that change to parameterization were. And finally, I'm going to end by just saying that there's no reason from what we've seen to suggest that the incorrect historical trends that we've seen won't continue into the future. We've seen that these changes to the mean bias appear to be largely linear across the period that we've looked at. And this suggests that any model trends that are analysed in both a historical and projected sense should be examined with great care. And I will stop there.
Before we start discussion, I'm going to do a quick mic check to see if they can hear us online. So check, check, Paul.
I mean, why don't we go ahead and use this microphone here? So we'll these question sessions have been nice, but they don't really seem to have been theatrical enough. So what we're going to do now is we're going to use this microphone for in the room questions. So if you want to ask a question in the room, then come up here. It can form a nice line, maybe going along here, and then maybe down that wall there, and then if we go kind of clockwise around the room. This is brilliant because I can just sit down and let the line run through. So,
I have a question for Jonathan. I mean, you argue that we could do things more cheaply with running them in S2S mode, but that's also kind of expensive to have a whole hindcast period. I'm wondering, do you think there's enough information to, say, take 5 years at the beginning and 5 years at the end to kind of get at the answers that you have, or something less than doing the whole hindcast suite?
Maybe. I mean, it's difficult because I think when looking at trends, you don't really want to be looking at a period shorter than maybe 20 years. But I haven't tested whether with the hindcast that we've got, if you take the first 5 years and the last 5 years, whether you see the same sort of thing. And if that is the case, then maybe you might be able to run a smaller number of initializations and then look at how the errors are developing within those initializations.
I have two questions. The first one is for Jonathan. So I think Don Smith, they did very similar things to use the hindcast to forecast the NAO. Did you ever check that, how to reconcile with their results? Because in your case, it seems like for seasonal temperature, precipitation, so they are quite different from the so-called signal-to-noise paradox.
Was the question, did we look at the NAO at all? Or?
Yeah.
We did. We debated about showing the NAO or the Arctic oscillation. They look quite similar. You see the same agreement in terms of the CMIP6 and seasonal forecast models between the two. But we did actually see something which did look like the signal-to-noise paradox in there as well, actually, in that analysis. Yeah.
I see. Thank you. Another question is for Li-Wei. So I observed, in your regression, so there are two clusters. The first the large cluster is in the bottom left, and a small cluster on the top right. So I'm wondering if you remove the top right cluster, would that affect your emergent constraint results?
So I did try to remove the top cluster. They are from MyRock ES2L and MyRock 6 models. So I did try to remove either of them, and the result would be similar. But if I remove all of the two, we will expect the result to be different. So but we believe more models could help us to get a more robust prediction results.
Thank you.
Just a quick reminder to the question askers to stand in front of the laptop so our virtual participants can see you.
Hi, this question is for Professor Ping Chang. So my specific question is on the decadal prediction of the Southern Ocean. So first of all, it's great to see the improvement of the model performance with the higher resolution. Then I also recognize for the Southern Ocean, you still have a very big region with negative or zero predicting scale. It seems to be common across some of the other models. So earlier I thought it must be related to either resolution, initial conditions, or some model physics. I wonder what's your take about how to improve the model scale in that region? Thank you.
Well, thank you for the question. I think Steve actually analyzed the results quite in detail.
Yeah.
And there is what we found is that when we increase the model resolution, there is a enhanced signal-to-noise ratio overall. And you're right. I mean, the improvement is not necessarily saying the high-resolution model is in a better shape. It's really the low-resolution model is so poor, so that when we compare it to the high-resolution to the low-resolution model, we see a much larger improvement. So the question really is that why the low-resolution model performed so badly in the Southern Ocean.
Yeah, great. On a positive note, most of our regions, we have good positive skills. It's just that only a small spot near the Southern Ocean. So good news. Thanks.
Real quick, I do want to note that we have quite a few questions online. Could we take an online question? Oh, that's you there. Good, great. We've got it covered.
All right. Okay. So my question is probably to Pedro, but to Pin as well. So in this response, this cooling, you see this nice subtropical cooling in this high-resolution model. However, if you compare the response along the equator, there is still the same problem compared to the observation. So the eastern Pacific along the equator is getting warmer, and this subtropical cooling penetrates too much towards the western Pacific. That's suggestive to me as a weakening of the water circulation along the equator versus the strengthening what's in the observations. Could you comment on this first? And the second part of this question, so especially to Pedro, so you emphasize this asymmetrical component of response and the observed trends. But if you look at the observed trends, a big chunk of it has a PDO pattern, a PDV pattern, quite symmetrical pattern. So that's another thing, if you could comment.
Okay. Yeah, I agree. There's not enough cooling on the equator. I mean, it's a lot better than in the low-res model. One answer could be internal variability. I cannot recall if your member number 9, the one that looks like observations, has, or 10. I mean, that could be an answer, but I don't remember. Does he have enough equatorial cooling?
Well, you look the Walker circulation index,
Yeah.
right? Southern oscillation index.
And I wanted to answer that question. I mean, at least the 4 members I analyzed, all 4 have a stronger Walker circulation, regardless how you define it, with an equatorial index or with the traditional Tahiti Darwin. So yeah, there's a bit of not enough cooling off the coast of, say, Ecuador in the far eastern equatorial Pacific, but it doesn't seem to be important to couple with the atmosphere, and that's reasonable, right? That place is too cold. The atmosphere will not know. But I mean, what this is saying is it's not the full answer what we showed. I think there's probably more stuff going on, perhaps freshwater forcing in the Southern Ocean that could make these responses stronger.
And what about the
Okay. What was the other question?
That was the second part of my question.
Okay.
Thank you.
I took too long?
Yeah, I have a question to like Jonathan and possibly to others. So like to me, it seems that high resolution is much better to like solve the problem for the tropical Pacific trend. But like when we see the like seasonal forecast model, I mean it is also high resolution model. Then why do they have it like still? So like is it due to this? I mean lack of the like response to the ozone forcing, or like yeah? Do you guys have any like opinion about that?
Yeah, that's a great question, and I was thinking about that earlier and yesterday actually, because yeah, these seasonal forecast models typically do have an ocean that's about at least 1/4 of a degree. I think C5 is 1/4 of a degree. So yeah, that suggests that resolution isn't all the answer, which I guess we all knew anyway. But yeah, it'd be really interesting to kind of dig deeper into why you do see the same trend errors in seasonal forecasts, but they are also run at quite high resolution.
Okay, I'm going to kind of paraphrase some of the online questions here. One from Gavin: is there a change in the ENSO variability in the high-resolution runs, or is it more of a kind of a mean effect?
To me, question?
Yeah, sure. Either of you probably.
I've looked.
The ENSO?
Yeah.
Yeah, I mean, we did some analysis for the long runs and for the PI control simulations. The ENSO, there is some difference between the high-res and the low-res, but it's not drastically different. And then the main thing is that the amplitude of the ENSO is slightly weaker. It's become more irregular. And also the period of ENSO actually tends to become longer in the high resolution.
Okay,
compared
interesting.
to the low res.
So a question maybe for any of you here, should we be going to 10th of a degree ocean resolution? And do we need to do that everywhere? That was one online question.
High resolution ocean everywhere?
Should we be
I mean,
thinking of
I think the
alternatives?
reason we decided to go with the 1/10 of a degree ocean everywhere is because we want to turn off the eddy parameterization. If you don't go to 1/10 of a degree, I think you run into the problem whether you want to keep the eddy parameterization or not, right? Because the model is going to tend to generating some eddies and then, but it's probably not enough. So it's you're in the tricky. I think it's going to be in the in the tricky situation.
Yeah, Pedro?
Yeah, and my answer is perhaps no. These simulations are so expensive, so we need to figure out a way to learn from them and improve the low-res models. It's just insane. Even if you want to do paleo or all these things that we are used to be doing, I'm not saying we should not have done this. I think it's great we did it, but now we need to learn from them. And perhaps the ocean, but the biggest cost is the atmosphere. So the issue is, right? The ocean actually is not that expensive to go.
It's not. It's not cheap, definitely.
Yeah. This
Okay,
stuff
maybe,
is not cheap.
Maybe one final quick question from online. Have you looked yet at the Arctic sea ice in the high resolution runs? Is there any difference there?
Yes, actually, speaking of that, we just have a paper accepted in the Nature of Climate Change, and there's a big change in the high-resolution model predicting a much rapid amplification, and mainly through the Bering Strait.
Okay, interesting. Right, I will leave the floor with my new laptop up and
Question / comment for Li-Wei. The leave one out approach for training model sort of assumes that the thing being left out is independent of the training data set, but we know there's model interdependencies. So I wonder what the implications are of that for how reliable the statistics are coming out of a leave one out approach.
I think that approach is mainly like if we want to test the machine learning is doing well, we need to test the models. But if we include that specific models in the training data set, the prediction will be good, and it could be because it learned from the exact same models. So that's why we have the leave one out approach at the first place. But when going to real analysis, yeah, I'm not sure if that's answer your question.
I'm just concerned that there may be models that look alike, and therefore leaving one out still will inflate. That causes the apparent performance of the AI approach to be inflated.
So you're saying like you're afraid the models look alike, like not different enough. Right. Oh, gotcha. Yeah, but based on like the scatter plot that we show, we actually did find like models like did have a structural difference between models to another models. But yeah, that's a good question and concern. That's we'll note to that. Thank you.
Hi, very nice set of talks. A question for Jonathan, or sort of an opportunity to expand on this last point. The way I kind of take it is like that this past period was particularly challenging for models because of their tendency towards their preferred attractor, which is not what's happened in reality. And so with some of the information we learn about the potential for this trend to reverse in the future, how should we go about using what you presented? Because like sort of by definition, then the seasonal prediction models will start to look better again, but you kind of show that they have fundamental biases.
Well, yeah, I think, in some cases they might start to look better, or the mean biases might start to, like you could see that on some of those time series the mean biases were reducing over the hindcast period. But it could be that those mean biases just flip sign by the end, like into the future, assuming that the mean biases carry on changing in the same way that they have been. And I guess that's one benefit of a longer hindcast period as well, is being able to kind of get a better handle on how robust these changes are. But yeah, I mean, it seems that maybe it's, yeah, like if the models are reacting incorrectly to maybe like some radiative forcing like CO2 or aerosols, I mean aerosols is probably more likely, then in that sense, I guess there's not really any reason to expect those mean biases to stop changing in the same way, if that makes sense, in the future.
I have a question for Jonathan. Can you articulate for me bringing the world of the signal-to-noise paradox and your world of this, seasonal forecast error? How are they consistent and linked? I just want to get a good picture.
What do you mean, sorry?
Well, the signal-to-noise paradox, I think, is probably giving the same indication of that you're finding that these trend errors are in the seasonal forecasts and the model mean bias themselves. Just how do we bring those two worlds together, Doug's talk and your talk? Are they the same thing? Are we talking about that the force response is too small? What are we? How are they?
I think you certainly see the result of the signal-to-noise paradox in the trend errors that we see.
Yeah.
But yeah, I think I'd probably need to think about that a little bit more. Maybe we could chat later today about that. If that's okay.
Okay. It feels like these are two big themes,
Yeah.
and I haven't. I'd like to. I feel like we should try to connect them.
Yeah.
Okay.
Definitely.
Thank you.
Yeah. Thanks.
I have two quite quick questions for Ping. So I see very impressive, the very significant difference between high resolution and low resolution simulations, but it seems only in the fully coupled simulations. But for the ocean only and atmosphere only, so the difference is not that significant. So do you think that could be due to the effect of interactions between atmosphere and ocean?
Yeah, that's a very good question. Yeah, I do think there's the feedback between the Southern Ocean SST gradient and the zonal winds, probably through Ackermann feedback, because in the high resolution model, the eddy is actually playing a less important role, looks like. And so a lot of the cooling is actually done by the wind-driven Ackermann flow. So I think there's probably a positive feedback between the two. That's probably the reason why we see a difference in the coupled simulation.
Yeah, and my second question is that, so I see you are mainly focused on the ocean and the southern hemisphere. So did you or any of your collaborators have analyzed some variables and response over land or in northern hemisphere, for example, land precipitation, temperature, or some cloud feedback to the changes in resolutions?
We did look the extreme precipitation. The high resolution model is doing a much better job than a low resolution model looking at the extreme precipitation. But yeah, if you're interested in that, maybe we can discuss that offline.
Yeah, sure. So I will leave time for Thanks.
Another question for Ping. I noticed, if I looked correctly, that in the high resolution simulations, in the future projections, the North Atlantic warming hole seems to disappear. Did you have an idea of why? And did you check maybe the oceanic heat transport in the northern hemisphere?
That's an interesting question. We have not looked at. I think we looked at AMOC changes in the high-res and the low-res. I think the rate of change is about the same. The AMOC strength in the high-resolution model is lower than the low-resolution model. So we haven't looked at these things in detail, but that's a really interesting question. Thank you.
Great. I feel guilty now for shutting off that discussion. Matt, did you want to come and say something in response to Clara? With a microphone.
Yeah, I mean, I guess to put a different spin on it and kind of answer your question. So we know these models have biases, and we know they develop very rapidly. We see this in forecasts all the time. They don't take years to develop. They take days to weeks. So what this is suggesting is that you run these models, and as you run them, you're changing the radiative forcing, and that mean bias, which is always present, is changing in balance with that forcing. It's not really a forced response in that way. And that change in the mean bias looks like a trend. And it looks like that the trends that we see in the CMIP6 models look like the mean bias errors we see in the seasonal forecasts. And so my zeroth order interpretation of all trend errors at this point is that they're not forced, they're bias errors. And that's a problem because as you go into the future, as you keep changing the radiative forcing in the models, presumably we're changing the mean bias in the models in a way that we don't understand. And so whatever error we're getting because of a changing mean bias in the future is a trend error, but we don't know what it is because we don't have a way to verify it as we do with the seasonal forecast. So that, to us, suggests that we want to do a much more extensive analysis of this type with seasonal forecasts because fundamentally we don't understand where the mean bias comes from in these models. And it's not, strictly speaking, a mean bias. More generally, this is going to be a difference in the model attractor and nature's attractor. And what this says more generally is that difference in the attractors, which is also in some sense going to be sensitive to the radiative forcing, is also changing. So that error does not have to be fixed. And the changing error, again, can look like changing trend errors in variance, prediction scale, pretty much everything. Right. Yeah. But in a system, but these are systematic errors. What's striking is how every single model seems to do this, and in a kind of an average sense. So it seems to be a mean error that seems to be endemic to basically just about all the models. So everywhere that John was showing significance, that was every model. Not just that it was significant, but every single model had the same error. So.
Okay, brilliant. Thank you very much. So let's thank all our speakers again and then let them go. And we now have our last set of virtual posters.
All right, our first presenter is Katharina Harmeth. Katharina, are you on and ready to share?
Yes, I'm here. I'm quickly sharing my slides. So hi everyone, I'm Katharina Hartmuth. I'm a postdoc at ETH Zurich in Switzerland. And on my poster, I'm presenting some work I've done doing my PhD on Arctic extreme seasons. And in particular, here in the study, we look at changes in Arctic seasonal variability and extremes thereof. And we have this very nice data set here at ETH where we have a CSM1 large ensemble. And we have, for 4 different periods, we have quite a lot of ensemble members, as you can see here on the left-hand side. And in particular, we have for a historic and a end-of-century period over 100 ensemble members, which gives us more than 1,000 years each of simulations, which is very nice if you want to work with seasonal extremes. And now I quickly want to show our key figure of this study. And so here we go. And what we show here are anomalies in the winter mean temperature anomaly along the x-axis and precipitation anomaly along the y-axis. And in particular, this is now for the high Arctic. And all these seasonal anomalies are with respect to the historical climatology, which is the dark blue. And what we can see is that in this region, we have this very strong increase in the seasonal mean, particularly in the temperature, but also in the precipitation. And then what we also see is with the contours that there is a change in the distribution of these winter mean values, but it is relatively small compared to the change in the seasonal mean. And now we compare this region with other regions. So for example, on the second panel, I show now an area which is already almost ice-free in the present day, which is the current Barents Seas. And here we also see this warming and wettening towards the end of the century, but we also see that here the variability in these parameters is much larger. And then there is this particular pronounced change in the temperature variability, which gets strongly reduced towards the end of the century. And then finally, we can link these changes largely to changes in the sea ice concentration, which is shown by the bottom panels. And for the left region, for the high Arctic, we see that basically in the historic, this is almost always ice covered in winter, and then it changes towards a more seasonal ice cover. Whereas in the current Barents Seas, we have already very little sea ice in the present day, and then this region gets more and more distant towards the sea ice edge in the end of century. So yeah, if you're interested in changes in this winter mean variability, but also how this is linked to weather systems, and also if you wonder how the CSM1 performs against a bunch of CMIP6 models, then yeah, please check out my poster.
Thank you, Katharina. Up next, we have Rosie Eid. Rosie, are you ready to share?
Yep, hello, I'll share. Great, thank you. Okay, so I'm Rosie Eid. I work at the Met Office in the UK, and I've also just finished a PhD at Exeter University looking into extreme trends in the winter North Atlantic Oscillation. The first half of my poster is showing results from our paper, which has the same title, Quantifying the Rarity of Extreme Multicadal Trends. And we talk about the lack of extreme NAO trends and multicadal trends in the CMIP6 and CMIP5 models, and show that this is consistent with a lack of autocorrelation, so the sort of persistence from winter to winter in the models compared to the observations. And the second half of the poster proposes a recalibration reddening method to try and fix this problem with the autocorrelation. So this first slide, I'm showing the winter mean North Atlantic Oscillation Index from the observations. And when I talk about extreme NAO trends, what I do is I take in this case, a 31-year window, and I calculate the linear trend on that window. And I do this for a moving window. So I get a whole series of 31-year trends from the observations and the models. And then I look for the maximum or the minimum trend in this series. So I've identified here the 1963 to 1993 observed trend. This was the maximum in the observed record. But if you compare it to the range of output from the CMIP6 models, you can see it was very unusual at this time and in the whole record. And in fact, if I do a stochastic model fit to the observations, this trend comes out as being a kind of a 1 in 20 event, whereas in the CMIP6 models, they underestimate this probability by a factor of 10. And this is consistent with a lack of autocorrelation. The models have a year-to-year autocorrelation of close to 0, whereas the observations, it's around 0.2. So I propose that we can try and fix this. We can apply a reddening filter. I suggest we use a first-order autoregressive model, or in particular a fractional difference model, to try and capture some of the long-range dependence found in the observed NAO. And here I've got box plots showing the distribution of maximum 31-year NAO trends in this shorter, most recent historical period. The grey is before reddening. This is the raw output from the models in CMIP6, and the red is after reddening. So you can see it's a useful tool for shifting your distribution of trends, leading to exceedance probabilities that better match the values we're getting from fitted stochastic models. But there's also the usefulness that stochastic models are kind of interesting, but we want to know what the model dynamics are doing and what are the external forcings doing. So this is a way of increasing the autocorrelation in the models, but also seeing how external forcings might affect our trends. Which leads me on to my final point, that it's important to think about all these problems in the historical simulations are also going to be important for future projections. So I'm showing here that for the high radiative forcing scenario or the low radiative forcing scenario, you can see that after reddening, we are shifting our distribution of maximum trends. So yeah, if you'd like to know more, please see my paper, see my poster, and there are plenty of references on the poster as well to similar work that other people have done. Some have presented here. So thanks very much.
Oh, you're muted.
Yeah, I'm sorry. Thank you very much for your help. Hello, everyone. Thank you for the opportunity to present our detection attribution work, focusing on the annual extreme rainfall. Detecting a human signal in the observed evolution of annual extreme rainfall is rather challenging due to the large internal climate variability, the limited observational coverage, and the large model uncertainty. Most studies so far did not focus on the role of aerosols and volcanic forcings, or only as a counteracting factor masking the effect of greenhouse gases. In contrast, Bill Collins yesterday showed a way to separate the fast and slow aerosol component, influencing extreme rainfall over CONUS. Here, instead, we focus on two large-scale mechanisms governing the global change in extreme rainfall. And we base our study on the, previous detection attribution results demonstrating that global changes in mean temperature and rainfall are governed by two main mechanisms. So the first one, capture in the middle, captures the global warming, the intensification of the red-dry rainfall pattern, and this mechanism increases over time as indicated by the black time series and is detectable in observation as shown by the red time series. It is mainly driven by the increase of greenhouse gases, partly masked by aerosols and with a clear cooling volcanic signature. The second mechanism on the right captures a pronounced interhemispheric temperature contrast governing the position of the ITCZ. This is mainly driven by the aerosol increase and is before and after the Clean Air Act, but also by the greenhouse gases and volcanic forcings. And this mechanism has a very complex decadal behavior, as you can see with the black time series, but it's captured also and detectable in observation. So the question we have is that can we similarly disentangle the impact of aerosol and greenhouse gases, but this time on extreme rainfall? Next, please. And in a nutshell, the response is yes. Using the pattern-based fingerprint method and CMIP6 model, we found a very similar behavior. The first fingerprint show an increase in extreme rainfall across the globe, mainly driven by the increase in greenhouse gases and a clear volcanic signature. But we also found a second fingerprint associated with the increase and then the increase of aerosol emission before and after the Clean Air Act, and also some volcanic signature. Next, please. We found that both behavior are detectable in the changes in extremes derived from the Reagan observational data sets, as you can see with the red time series. Next, please. And we also found that the model with high ECS and with finer horizontal resolution correlates slightly better with the observations that model with a low ECS and coarser grid resolution. So if you want to have more detail about this work, I invite you to look at my poster or please email me. Thank you very much.
Yeah, my name is Dirk Olonczak from Max Planck Institute for Meteorology. I think you've seen that plot already on Wednesday in Maria's talk because she gave a brilliant introduction to our study. So we find that coupled climate models systematically underestimate the radiation response to surface warming. And what we find, first of all, is shown here that the global mean top of atmosphere radiation trend, the observed one, is systematically underestimated by 11 different large ensembles. And we show that this is not because of underestimation or overestimation of the surface, global mean surface warming. But how can we understand, why do we find this consistent underestimation of the top of atmosphere radiation trend? To understand this, we look at the spatial patterns, and we always look at the discrepancies between simulations and observations, here shown for the top of atmosphere radiation trend. And we then have a similar pattern for the surface warming trend. And then we relate these two discrepancies. So the discrepancy in surface warming and the discrepancy in the top of atmosphere radiation trend, here shown for one average of a region, subtropical Eastern Pacific response. And what we then do is to calculate an orthogonal regression through these discrepancies across all the different models. And then we interpret this y-intercept of the regression line as the response bias. So for a correct surface warming trend, what's the response bias of the top of atmosphere radiation trend? And then we do exactly this for every individual grid box and get this kind of map where we find that the top of atmosphere radiation response is underestimated in larger regions and with a larger magnitude than in regions where we have overestimation. So this 2-week local coupling between surface forcing and top of atmosphere radiation results in the consistent underestimation of the top of atmosphere radiation trends. So we find that climate models consistently underestimate the observed global mean top of atmosphere radiation trend during that period because they underestimate the local coupling between surface warming and the top of atmosphere radiation. But why do they underestimate this local coupling? So we test the contribution of two different aspects. So first, errors in atmospheric physics or differences in the surface warming patterns. And to disentangle the two, we look at AMIP simulations. So we have to look at the shorter period, 2001 to 2014 only, and are limited with the number of AMIP ensembles that we have. But overall, we find that the result is very model dependent. So some models like MIROC 6, IPSL, even with the prescribed SST pattern, they still underestimate the global mean top of atmosphere radiation trend, implying that errors in atmospheric physics matter most. But for other models like SCAN-ESN5 or ACCESS, we find that with prescribed observed SST patterns, the top of atmosphere radiation trend is more correct, implying that the realistic surface warming patterns matter. And finally, we relate our response bias metric that we introduce to the effective climate sensitivity of the different models. And we find a relationship between the two. So low ECS models have a lower, smaller response bias, so they better represent climate change over the last 20 years than high ECS models. Yeah, for details, please check this, our recent paper, or go for my poster. And yeah, you can also message me whenever you like. Thanks a lot.
Great. Thank you, Dirk.
First, our finding suggests that the TOE for Korea's peak summer temperature could range from the 2010s to the early 2030s under the SSP 585 scenario, indicating that we may already be experiencing the effect of global warming. When the long-term trend is approximated with the CO2 concentrations, the DOT is pushed back from approximately 35 to 70 years beyond the one based on the linear future trend. Throughout analysis, we discovered the peak summer temperature in Korea were an overestimation of the long-term trend and the underestimation of the natural climate variables. By flooding the regions, global annual temperature overestimate both natural climate variability and long-term trend. Ultimately, our research led us to three conclusions. First, the TOE for Korean peak summer varies significantly from the 2010 to the early 2013s based on the SSP 585 scenarios, indicating the TOE is already passed or is immediate. Second, earlier estimated TOE could be attribution to the biases that climate models tend to underestimate natural climate variability and overestimate the long-term trend during the peak summer monsoons of July and August in Korea. Third, the low emission scenario highlighted a significant delay in the TOE when compared to the high emission scenario, emphasizing the crucial role of reducing greenhouse gas emission in addressing the impact of climate change. Thank you for your time.
All right, hello everyone. This is the final session where we want to summarize what happened in breakout 3 and then also wrap up with a few final things. So I realize you haven't had a whole lot of time to kind of synthesize things from the third breakout. So thanks to all the people who are willing to present on this anyway. So I guess we will, is it sharing on the online? Can you see on my laptop? Yes. Okay. All right, so we'll start with room 1. Oh, is that you? Oh, okay. I know.
Maybe they didn't make it in here.
Okay, it might have been. Okay, yeah. Room 2.
So in room 2, our approach to addressing the charge was to, from the list of bad, mostly from the list of bad things from day 1, we picked out a few things that we thought were most important. Specifically, I don't remember whose talk it was that had the pyramid of the things that are important for lots of the climate system, and then increasingly more specific as you go up the pyramid. And so we were focused on the things that are going to affect a lot of other things. That's how we prioritized. And so the things that we came up with that are that we thought were important were the Southern Ocean SST, equatorial sea surface temperatures and the Walker circulation, large-scale gradients like Arctic amplification, clouds, AMOC, the carbon cycle, and ocean stratification. We came up with some specific issues that are currently inhibiting analysis. A strong theme was that we could use more observations or better observations, better observational continuity, for example, the satellite missions going one after the other. Also, for some of these, like the carbon cycle, there's structural problems and missing processes in models. And then decadal variability and how to figure out which observations to use, which reanalyses to use or not use, and how to justify that. Then the next proposed steps and things that maybe we could do are use higher resolution models like we've seen today, apply complementary theories. So like if we've been thinking about something from one framework, like polar amplification, we can think about it from a different framework. Like instead of the radiative convective theory that makes a lot of sense in the tropics, think about the radiative advective way of approaching polar amplification. More observations, keep taking observations, harmonize the data treatment for comparability, and implement more processes in models where appropriate.
Do you have, oh, it's there? We might have to. Yeah, do we have to pull it from the? Just one second. I can do this really quick. We'll just do it from here. Okay, group 1.
Okay, so we said that the tropical SST patterns and circulations and its impacts on the climate and ocean heat uptake are a high priority, and they're also relevant to radiation and wind, which was another topic we had discussed. The water cycle, hydroclimate more broadly, top of atmosphere shortwave and long-wave radiation, and as that relates to setting temperature patterns, near surface humidity trends as it relates to Isla's work. Ice and sea ice is important for the ecosystem, sea level rise, polar amplification, deciding, we had a fun conversation about the signal-to-noise ratio, and we decided that a high priority should be deciding whether or not that exists before we can dive into that. And then for the second question, thinking about diagnostic packages and how they should maybe expand to include trend metrics and needing more uncertainty estimates from observations. We came back to that a lot. One really cool idea was kind of to understand the origins, thinking of hierarchy of theory and modeling, starting at your more simple dimensions before you make it more complex, and so adding that level of complexity, see where the discrepancy comes out. What is stopping us from going through the best practices for those that have not been looked at in enough detail? We said resolution, just like group 2. Ice sheet modeling came up, and then coming back time and time again to observations and these uncertainty estimates that go with them.
Okay, group 3.
I see why you're looking there. It's not here. Okay. Yeah, we discussed some high priority mismatches or identification of whether trends are in the observations, and our models capture it as the pattern effect, which we didn't talk about that much as instructed. Then we mentioned the large-scale atmospheric circulation, such as shifts in the head decel, aerosol forcing and response, where we don't really have that great observations, so it's really hard to know what the models are doing and whether the models are doing something correct. Sort of similar for cloud feedbacks, and observational uncertainty attributions go along the same lines of what has just been mentioned, that we need more observations and we need to know the uncertainty that comes with those observations. And then humidity over land was, for example, an example where we probably need observations first before we can attach uncertainty to those observations, because apparently we really don't have any observations. And then we had a bit of a discussion about whether regional impacts should be lower priority than global patterns, and we talked a little bit about whether regional impacts were something that was more refined than the large scale, or whether the large scale is an integration of the regional patterns, and I don't think we came to a conclusion there. Yeah, proposed methods to alleviate this was, we had a good discussion about needing more observations, as has been mentioned before, and again, uncertainty with these observations, and we need to make sure that we understand the observations that we have and make best use of the available observations and observations as they become more available. And so we talked a little bit about the NCAR Climate Data Guide, to use it, for example, to find the observations that would be useful for you. And along those lines also about diagnostic packages, which have also been mentioned before, so that people can easily use a package to make use of the data that are available. Kevin, do you want to jump in?
Yeah, I guess I can sort of finish the list here. We talked a lot about kind of how to sort of improve parameterizations in models, and sort of a model hierarchy, which is common in the large-scale dynamics community and the cloud community. We're saying that that would be helpful maybe in other communities as well. And then potentially using AI methods on those sort of simple models to try to maybe think about new ways to develop parameterizations. We talked a lot about tools, climate dynastic tools, like is there a community package that could be put together to help people sort of isolate forced from internal, and that's kind of what Rob is doing through the force SMIP. So I'm trying to think if there's anything else. What's that? Model hierarchy. I mean, I think that was kind of the yeah. So I think that's everything. That, and we had to move in the middle of our breakout, so that was the most exciting part. So.
Yeah, I admit I opted for talking to more people about their poster versus typing up our notes. Yeah, as expected, we have a lot of, or some overlap with what said before. We did kind of like a simple going around the room, so we hear a little bit from everybody. Yeah, we asked them what the most important process is, but inevitably, I think this is always a little bit biased by what we all were working on. Still, sort of SSTs as a summary, metric, I think focused a lot on the Pacific, came out on top. Top of atmosphere imbalance pattern, also components, short wave, long wave, that those are important things to confirm trend discrepancies and understand processes. And then not just Arctic sea ice, but sea ice trends more generally, Arctic climate as an important component of the Earth system. Regional temperature and precipitation, actually to be more precise, we talked a lot about extremes as just a fundamentally societally important metric as well, that in a warming world we might see more of those regardless of exactly how much we warm. And so that's an important, more regional focus. And then wind speeds, again, that's an impact metric, but I think then we went on to kind of like tie that in with large-scale atmospheric circulation. And so then on our second slide, I kind of came up with this non-perfect way, I think we'll see a better one on the next slide from another group, to like match this up with our draft protocol, right? Do we have a like-for-like comparison for SST trends, TOA, temperature and precipitation extremes? And it's a bit of a mixed bag, and we don't have to walk through all of this. But yeah, for some things we have confidence to, and all the tools we need. For others we don't, as expected. I wanted to mention ocean circulation and mixed layer depths, or stratification, I think was mentioned before as well. I think that's, a lot of people think that's important. I feel like in the talks we've seen it might have not been at the forefront. And then sort of to the last point of the charge, what are issues? Forcing uncertainty is something that we discussed a little bit that I haven't heard yet. And then we had a bit of a sort of a discussion of the trade-offs between investing in model resolution versus like, do we feel like we finally have enough large ensembles? The desire for single forcing ensembles was mentioned by some to actually better understand what's going on in our coupled models. And then under reimagining model experimental setup, we had a couple of ideas to make computation more efficient, given that we kind of are going to higher resolution. So there's some sort of software engineering ideas. And then we also had a sort of a climate model data guide idea, but focused on trends, or adding maybe a trend interpretation component to the climate data guide. And then finally, consistent with others, sort of confronting observations with observations in the spirit of this workshop.
Okay, group 5.
You see that we have followed kind of similar approach to the rest of the groups, that we were reviewing what were all the variables that were identified that has a bad state in comparison with models, and trying to prioritize them. And so we were dealing with the fact that, we are affected by the subjective impression of which are the importance of these variables. So we were trying to find a more objective way to analyze that, and then we tried to prioritize the variables in 2 dimensions related with the global importance and fundamental importance of these variables, and also the ability to be assessed. And so then on the right corner, we find the East-West Tropical Pacific SST gradient, because we have also, all of us, we have recognized that it's a very important variable, and that we already have a good data set to assess which are the origin of these discrepancies, because we were not, you will see at the end that we have not proposed like new methods, because we were focused on trying to identify which were the variables that we can apply the methods of the best practice that were defined yesterday to follow, to measure which are the discrepancies and which are the origins for these discrepancies. So, as I said, in the right corner you have this zonal gradient of SST. You can see that, for example, Southern Ocean SST is lower in the ability to be assessed due to, well, the lack of observation in the pre-satellite area. That means that we are not so sure about the discrepancy because the time series we cannot be so confident on that. Some of them you have also find in the other groups, like the top of the atmosphere radiation that has some kind of similar problem. Then in lower order or if importance, we have also found Arctic amplification and sea ice. We recognize the global importance of that, but it's in a lower level and is more difficult to be assessed. And the tropical upper tropospheric temperature, yeah, it was said that observations are tricky. This is not my kind of expertise. The aerosol composition we recognize is really, really a very important variable, but it's very difficult to be measured and assessed. And we listened this morning the problem with the land carbon source and sink, which is very important, but it's really, really difficult how to get the observation from that. And then that was based mainly on what was identified as bad, that we were sure that there were discrepancies the first day, but we were also asked to look for the variables that perhaps haven't been looked in enough detail, and we can have an opportunity for that. Then is the second? Okay. Okay, and then you have the same variables that we identified in the previous one. You see that some of them have passed from the upper right corner to the lower down. Because what is now in the y-axis is the ability to be understood from the models, what are the sources for this discrepancy and the trends and so the Arctic semi-Arctic humidity was higher in the ability to be addressed or assessed due to good coverage of measurements, but it's more difficult to be understood. And we have the top of radiation that goes also in the other direction. The east-west tropical Pacific SST gradient remains in the same place. And I think we add some, I don't know why they are. I think we had some variables that were in the previous slide. Is it? Maybe not. I suppose that we had some variables that weren't in the previous slide. I'm incorrect?
I think they're all the same.
Okay, I thought we add some of the variables that were not in the ones that were identified as bad, but that were to be assessed. But I don't remember which were they, in fact. I don't know if someone from the group remember. Yeah. Okay. Okay, that's all. Thank you.
And then is there online? Oh yeah. Okay. Is someone online going to present this?
Yeah.
Okay.
Yeah. So we didn't really break specific variables by priority, but we thought the highest priority should be with variables that have well-known and trusted observations, while the lower priority for things with limited observations or observations that have large error. Additionally, we thought observational trends that are on the edge of ensembles should be looked into more. Are they truly on the edge? And then in terms of methods, maybe not only relying on ordinary least square trends, but using more remote robust methods, especially when there's large uncertainty. In terms of things moving forward, taking advantage of the most up-to-date observations, as they've been improving since the end of the CMIP runs, and stitching together scenario runs to the historical runs adds additional uncertainty, which should be maybe avoided. So maybe we should push for updates to historical runs. Additionally, we need to take into account what models can resolve before deciding if there's a discrepancy, and maybe move towards higher resolutions. And then lastly, as said before, some things we just need more observations before going into the full details.
All right, thanks. Is there another virtual breakout? Or okay. Yeah, thanks for those great summaries. I guess we have a few minutes if anyone has anything they want to say to reflecting on the breakouts. I mean, it seems like there was quite a lot of agreement on what's the most important thing and what we need, so that's good. Should we just go with the wrap up then? Okay, so oh, right. Okay, so first of all, we have a lot of people to thank. First of all, thank you all for coming, both in the room and online, and for all your active participation and all the discussions, both after the talks and in the breakouts, and for all your presentations. So I want to give you all a round of applause. Thank you. Also want to thank all of the organizing committee members who've been participating in telecons to make this come together for quite a while now, and for all their efforts during this week, and also all the people that volunteer to lead breakout sessions and report back on the breakout sessions. So thank you all. Also want to thank our sponsors who we mentioned at the beginning, but that's US CLIVAR, NOAA, NSF, and NASA, who gave a lot of funding to allow us to bring all the invited speakers and to also fund the travel for many of the early career participants. So thanks to them. And then we have Mike Patterson, who wasn't here in person, but I know he was listening online, and he's been very happy with all your participation. So he really allowed us to have this workshop and made this happen. So thanks to Mike. And then we have Alyssa, who has been really instrumental in making this workshop happen, both in the planning stages up to now, and then throughout the week, in making sure everything runs smoothly. And also in going really above and beyond and transitioning to this location, which I think made everything more difficult, but everything went very smoothly because of Alyssa. So we also have something for Alyssa, just to thanks for going really above and beyond. And we're so happy that we got to be here in person and not in our houses and hotel rooms online for 2/3 of the workshop. So thanks for that. And then also in a similar vein, Carrie Dawn, who I think really was instrumental in getting us here to the Embassy Suites. Our local organizer who organized the workshop up at the Mesa Lab and then moved it all down here, and managed to really quickly make the decision for us to come here and also for us to stay here today, which is good because the Mesa Lab is still closed. So thanks a lot to Carrie Dawn for all your efforts. And then also behind the scenes, we've had Paul Martinez and Nick Rempel, who you would have seen them on the first day up at the Mesa Lab, the AV help there, but they've also been helping to make it go really smoothly, transitioning to the new system here in the embassy suites. So thanks to them. And then we've also had some help from Xavier, who's the AV help in the embassy suites. So thanks to him. And then we also need to thank the embassy suites and also the people who didn't make it to the embassy suites and who were supposed to have a conference in here, I believe. And we took their food and their room. So thanks to them. Okay, so I think we remembered to thank everyone, and I'm sorry if we've forgotten anyone. So we have a bit of a wrap-up of things that we think we've learned, and we're definitely happy to hear any other thoughts of what you've learned that might be different from this. So this is not necessarily in order of importance, but things that have kind of been a constant theme throughout the 3 days. We learned a lot about the resolution can matter, so maybe there's some hope there. We can move to getting more trends correct if we move to higher resolution, although it's not guaranteed. I think there's maybe some hope to understand things a bit better using more initialized predictions, and we heard about that in Jonathan's talk earlier this morning. Forcing uncertainties is not all about necessarily the models being wrong, but the forcings can have issues too, so that's always something we need to consider. I think everything benefits by more understanding, so when we have discrepancies, if we can understand why they're happening, we can be much more confident in what's the cause, and then also we can try and understand what we need to do to fix them. Of course, in many cases, internal variability can be large, and that's always something we need to factor in, although maybe there are some regions of the world or trends where that's less of an issue, and so that's useful. Maybe there's some metrics are more robust than others, and maybe we should be trying to focus on metrics that are robust, where we're confident that the observations are good and there's not spurious trends. So I guess one thing that came up that I hadn't really thought about before is this kind of difference in what we need in terms of scientists in quantifying discrepancies in trends versus what people that are using climate model data to inform decisions might need, and that's not necessarily the same thing, so we have to think carefully about how we communicate things there. And then I guess part of the understanding issue is, it's very helpful if we can figure out, are we getting the forced response wrong, or are we getting the internal variability or the magnitude of the internal variability wrong? And that can be really challenging in situations where the force signal looks like modes of internal variability. I thought maybe it's on one of the other slides that you're going to go through, but I think another thing, of course, is the observations that came up in everyone's breakout groups that, we need to have good observations. So I will hand it over to you to go through the next.
So where did the observations end up?
Yeah, I don't know. Oh, reflections, maybe it's
okay, yeah, it's there. So just as a kind of summary of the next steps, after we've spent this wonderful 3 days together learning so many things, and I should highlight that at some point when someone came by to clean up my dishes, they said, everybody's so happy, everybody's smiling in this room. And I'm like, yeah, there's a lot of energy. It's been really amazing. So in terms of next steps, we're going to write a report for US Clever about the meeting, and so we'll be happy to share that with all of you. That is guaranteed as part of having them help fund and organize this workshop, and so you'll see many of your thoughts in that report. That's why these breakouts were so important for us. And then our objective, as we also said in the introductory material at the beginning on Wednesday, is to also try to synthesize this for a perspective or review. This is clearly a very bottom-up and exciting topic, even though it's revealing some discrepancies and things that maybe weren't expected. but should be summarized. And so that's what we're aiming for. And then as a broader community effort to try to move forward, US CLIVAR has working groups, so that's something on our mind, and certainly interested to hear your thoughts if you're interested in thinking more about that. So as always, please get in touch if there's something here that that's of interest to you. In terms of reflections, I think one big takeaway was, and it's been said a few times, maybe there weren't enough observationalists in the room for the past 3 days. And that's, of course, very important to think about, how we can have more interactions across modeling and observational communities to get a handle on the uncertainties, and, of course, to also upscale the efforts to continue to monitor. I know in the US especially, there's always challenges in Congress to pull funding from satellite programs and so on. So the more we can come together as a modeling and observation community, the better. And I guess another issue is to train and interact more with climate model developers. So creating tool packages that have been suggested so that our information can go into model development and we can see, the progress, which we, always see. But I think the trend discrepancy issue can be another source of information for improving models. One thing we've discussed is to potentially continue this interaction through AGU or AMS sessions or EGU sessions, where we continue to get together and kind of hear the latest results. I think discrepancies will take a while to figure out, so it might be great to continue that interaction with these more regularly scheduled conferences. The final thing we want to say, and then we can open it up for discussion for people who want to say a few words in addition, was in the online chat there was this kind of nice exchange about reflecting on the state of the climate, which is a bulletin of the American Meteorological Society. And Kate Willett had this idea of, wouldn't it be great if we had something sort of similar for trends? It's a really big effort to think about, but something we wanted to share with you all because it was really a great discussion in the chat. So I'll leave that up there for you to think about, and happy to hear any of your final reflections. And I think that's all that we had planned. So thank you again for your participation.
Yeah, I just wanted to say that this last point sort of overlaps with one concern I have, which is all the discrepancy we've been talking about are known discrepancies. We don't know what the unknown discrepancies are, and in a sense it would be useful to have sort of a hierarchy of the model characteristics, or characters that have outputs arranged that in 2 dimensions, how well the observations can challenge them and how important they are for what we need to know about the climate system, so we can find what the gaps are in our knowledge of discrepancies.
As one of the few observationalists in the room, and also touching back on the discussion we had last night, we were talking about the importance of really being frank about what observations means, because people who do in situ observations put a lot of sweat, and in case of seeking oceanographers, they also put in vomit to get that data. And it's just, it's understandable that people want to make comparisons to global data sets that go back to 1850, but I think sometimes it might be important considering that let's just try and figure out how we can make the most insightful comparisons using in situ real data that we know we can trust. And another issue that came up was, even if that data is being assimilated perfectly into reanalyses, then there's an issue of fairness, because once a person makes the observation and publishes the observational data that gets put into a reanalysis, then they no longer get credit for the hard work they did. Only the reanalysis people do. And that's another thing to consider. Thank you.
Any other thoughts? You don't have to come up here. I can bring this mic to you.